Hi and welcome to the training course for the AWS Certified Solution Architect Certification Associate 2020. This course is meant to help you acquire the competence required in order to pass the certification. This training is 24-hour long and is quite complex. We'll cover numerous concepts that are extremely interesting and that can be transposed on our businesses. In order to better understand this course, it's necessary to have a few notions in IT. This preparation course will include videos covering each model and its associated documentation. Amazon offers more than 90 services to its customers. However, we'll focus on only 30 of them, in particular those relating to the management of infrastructures. You might wonder what AWS is. AWS is the cloud platform owned by the Amazon Group. Today, it allows companies and consumers to have access to servers and services such as load balancers that are easily scalable and manageable. Since its creation in 2006, AWS has become one of the main actors in the market. In 2017, AWS offered over 90 services to its customers, working for many corporate leaders such as Netflix and the Amazon retail site itself. And of course, there is other companies that are using the Amazon Web Services. What are we going to learn for this course? As explained before, we will explore the 30 main services that allow us to control and monitor an infrastructure on the AWS platform. There is no need to focus on the acronyms of these services, since we'll come back to them later on. Now let's move on to the creation of our AWS account. To do so, go to the AWS website. Once it has loaded, click on Create an Account, and this takes you to the account creation form. As you can see on the left side of the screen, AWS account offers 12-month access to the free offer. To better understand how this free service works, I advise you to visit this link to see all the details regarding these free offers. As you might have noticed, there is 3 types of services. The ones that are always and that remain free, those that are free during the first 12 months, and finally the free trials. You can find the detail of these free offers here using the filters. As for us, we will remain only on the free services for the needs of this training. Let's get back to our form. To create your account, you need to enter an email address, create and confirm your password, and set a name for your AWS account. Once completed, this takes you to the contact information. You can choose between professional and personal, but your account has to be set as personal. You then have to fill in a telephone number, a country, and address, that is to say, usual information. You must then enter your credit card information. Your credit card information will only be used if your use exceeds the free limits. When this is done, we can then connect to the console. Now we'll create our first AWS budget. To do so, access your console. When you click on Build, the billing option appears. By clicking on it, it leads you to a budget page. where you can find on top the expenses of the month, currently at $0. To make sure that we never exceed the content of the free offer, we will create a budget. We can therefore create our first budget by selecting the cost budget option. It has to be given a name. You can choose, for example, AWS training course. Set the period to monthly and the budget effective dates to recurrent. For the date of beginning, choose the current month. You then have to define the amount of your budget. $10 is usually a good start, but it all depends on how much you're willing to invest in your AWS training. If you don't want to spend any money beyond the free package, you can set the limit to 1 cent. From now on, you are sure not to spend more than that amount on AWS, that is to say, a cent. The rest of the settings are optional. Once you're done defining the budget, you can set the alerts. We can define the way of sending our alerts depending on the real or forecasted costs. To be certain to never spend more than the amount defined on the previous page, it is necessary to click on Real Costs and to set the alert threshold to 100% of the forecasted amount. All that remains is to define the person to contact in case that amount exceeds. We can then confirm our budget. A recap appears. It indicates our monthly budget and also the estimated amount never to be exceeded. In this case, 10 cents. Once we confirm this information, our budget is created. If my budget exceeds 10 cents, I am sure to receive an email. During this training, you're not meant to spend money, but in case a mistake is made by, for example, leaving a few machines switched on, it can lead to additional expenses. In that case, you're certain to receive an alert so that you can control these extra costs. In case of an overspend, you can go to your bills and get a detailed breakdown of the billing. We are now ready to start the AWS training. We can now start the first part of this course. First, we will learn the differences between a region and an availability zone. Later on, we will see the advantage of regions and how they are spread around the world. We'll also look at IAM, that stands for Identity and Access Management. It will show us how to manage users, the access to resources, and the security strategies. And then we'll study EC2, Elastic Cloud Computing, the tool the most used by all companies and developers working with Amazon Web Services. EC2 allows users to manage resources, services, integration, and the network. It is the most popular tool when using Amazon Web Services. AWS is a global cloud platform, therefore it has data centers all over the world. These data centers are called regions. As you can see on the map below, the regions that are already active are shown in blue. and those that are being created are shown in orange. To identify these regions, there is a naming convention. If we take the example of the EU West 3 region, the data centers available are going to be those in Western Europe. Whereas if we take the example of the US East 1 region, the data centers available are going to be those in the east of the United States. Regions are made of multiple data centers, and therefore most of the Amazon services we'll be using in this training can be regional services. This means that a machine running on one region is very likely to not exist in another. In the console, you can see the geographical area associated with each of these regions. For example, AP East 1 is in Asia Pacific and its region is Hong Kong. Each region has several availability zones, often 3, with a minimum of 2 and a maximum of 6. If we take the example of the Sydney region, called AP South is 2, there are several availability zones. AP South is 2A, AP South is 2B, and finally AP South is 2C. They form a region broken down into several availability zones that remain far apart so that they are isolated in case of a disaster. Although they are geographically isolated, they are linked by a high bandwidth, low latency connection. This guarantees a very high availability for each region. Now let's see how it presents itself on the console. We'll be able to find the information regarding the zones in the small drop-down list at the top right. As you can see, there is a large number of them in the United States, in Africa, in Asia Pacific, Canada, Europe, and the Middle East. For this course, I invite you to select a region that is near your location. If you're European, select a region in Europe, and if you're from the United States, a region on the American continent. This will allow you to have a better experience and a better validity regarding the display of the different services. For example, I'm currently in Paris. If I want to access the EC2 console, the response time is increased. If I'm in the United States and California, and I launch the same EC2 console, the process takes longer. There is a real difference when you are very close to your region and when you are very far from it. As we saw earlier, EC2 is a regional service. For example, if I create a resource in California, it will not be available in the Europe-Paris region. On the other hand, if I go to an AIM service, right here we'll be able to see the list of regions, meaning that we are going global. All the modifications that we can make in the management of users and accesses will be applied at a global level. In other words, they will be effective for all zones. We will now look at how the global AWS infrastructure works. It is important to understand how the company is organized in order to use AWS in the right way. As you can see, we already have 24 regions launched, 3 regions announced, 77 availability zones, 1 local zone with very low latency application, twice as many regions with twice the availability of the second largest cloud provider, 245 countries and territories served, 97 direct connect locations, as well as 216 points of presence around the world. If we go down a little further, we'll find a map of all the regions, and by hovering it, we will find the information relating to the availability zones for each one of them. For the needs of this class, I strongly advise you to choose a region that has at least 3 availability zones. For example, if we look at Beijing, there are only 2. It is better to choose another one with 3. In my case, I'm located in Paris. There are indeed 3 availability zones. Another thing I would like to show you is the Regions and the Zones Availability tab. The details that appears is related to each area. You can find the information you need regarding North and South America, Europe, the Middle East, Africa, Asia, and the Pacific. By scrolling down a little bit, you'll find the information related for each region in the availability zone. The East United States region is located in Ohio with 3 availability zones. You can find details regarding all the regions in the world. One last thing I would like to show you is the region table. This table will allow us to know which AWS service is available in which region. For example, if we look at the Alexa for Business service in the United States, this service is only available in North Virginia. So, if you are in a region where a service is not available, like the Amazon AppStream 2.0 being not available in Ohio, in that case, if you need a service that you can't find in your region, I invite you to check this table to verify its availability. In this section, we'll cover the IAM service, which stands for Identity and Access Management. It's the service that allows users to manage the rights of AWS. All aspects of security will go through this service, whether it is for users, groups, or roles. The root account must not be shared with any users. It is only used during the first installation to create the first users. The IAM service is the heart of AWS. You'll be able to manage all aspects of security from the IAM platform. The security policy are written in JSON. I will teach you how to write this way in this course. We will try to have a micro version of the functioning of the IAM service. In general, IAM and AWS are divided in 3. There are users, generally physical person, groups that can contain users grouped according to their function, business, or team, and roles that define the internal use of AWS resources for each group or users. Security policies allow us to define what user groups or roles can do and cannot do. As we have seen earlier, IAM is a global tool. Decisions and settings in the IAM service will be reflected in all of our AWS services. Our permissions are managed by group policies written in JSON, and it is possible to set up strong authentication methods such as MFA, multi-factor authentication. Later on in this course, we will see the implementation of group strategies and their writing. Usually, large companies have their own IAM user database, so users can log in with their company account. Identity management uses the SML standard, which is widely used in directories such as Active Directory. Finally, I will remind you of the best practice for managing user accounts in any structure. There must be one IAM account per physical person. There should be a single IAM role per application. Login information should never ever be shared. And you should never write your IAM credentials in your code. You must never use the AWS root account except for the initial installation, and never use the IAM root account. It is generally recommended that you create new accounts and then block the administration accounts. In the next module, we'll see how to create users, groups, and roles. In this part, we will discover what EC2 is. First, it stands for Elastic Cloud Computing. It is the most popular service of AWS, and it will provide us with the ability to run virtual machines, store data on virtual disks, distribute loads between several machines, and scale services using auto-scanning groups. Understanding EC2 is fundamental if you want to understand how the cloud works. In my opinion, it is the heart of AWS, both for managing your machines and all the associated services. Let's embark on an exercise. We'll start our first Linux machine. To do so, we'll launch our virtual server and choose its type and the system to install. Today, we'll see the different parameters relating to our instance, as well as how to launch and stop our machine and terminate it. So here we're on the console. We are going to look for the EC2 service. As you can see, here you have the EC2 service. As explained before, when launching an instance, you have to be extremely careful about your location. In my case, I'm in Paris, so I'll be launching my instance from Paris. As you can see, in Paris, I have no instance running, no dedicated votes, no storage, no key pairs, no placement groups, no elastic IP, no snapshots, no load balancer, and finally, one unique security group that is set by default. To launch it, you need to click on the tab Launch an Instance, For the purpose of this course, we'll use the Amazon Linux2 AMI image, as it carries with it many Amazon-specific services that we will need during this course. In addition, this image is eligible to the free offer. We can apply the free offer filter to ensure that only free offers appear, and as you can see, we can find the AMI that we've selected. Once you have selected the type of system to install on your server, you can select the type of instance. There is a very large list of all the type of instance that can be launched. The main differences are about the resources available, that is to say the vCPU and the memory. Here with the T2 Micro, we have one vCPU and 1 GB of memory, which is more than enough in our case. Once the type of instance selected, it could be launched. However, it is preferable to see the different parameters that can be applied to have a more global vision. We are now at step 3, where the details can be configured. We could launch, for example, 3 machines, but in our case, it is preferable to only launch 1. Regarding the purchasing option, it is possible to make spots instances, but here it's not necessary. Here we'll use an on-demand version, meaning that we'll create a machine depending on the demand. At the network level, the VPC, the virtual private cloud, defines the network on which your instance will be located. The subnet defines the availability zones on which your machine will be located. It is preferable to select the default option. Concerning the automatic allocation of the IP address, you should know that if you leave the settings by default, the status setting will be defined as activated, and therefore we'll have an IP address that will be allocated to us automatically. However, you could change this setting. For the time being, we do not need either placement group or role IAM, and we will study later the capacity reservation and the stop behavior. All these parameters are correctly defined. There is no need to change them. In terms of advanced details, it will be interesting to see later on how the user data is used. For the moment, the parameters are well set. We then move on to the next step, the ones where we add storage. Our operating system, our AMI, must be installed on a hard drive, and it is at this stage that we will define the size of the storage. It's not necessary to modify this size since Linux systems do not need more than 8 GB. The default capacity will be more than enough for the purpose of our tutorial. It is possible to encrypt the hard drive, but it is better to keep it simple. We then click on Next. This is where you can add tags that are used to identify our machines. For example, we can put next to the name tag the name of first instance. We continue with the configuration of the security group. We'll define which ports are open to our machine. It acts as the firewall of our machine in AWS. Since we are creating a Linux machine, we will be connecting through SSH. So we'll create our first security group, which once again I will name my first instance. In the description, you can, for example, write my first Linux server. You then have the type of SSH, of TCP protocol, the range of the ports 22, as well as the ability to create a private IP address, something custom, anything that you desire. Here, the address quadruple 0/0 means that we can connect from anywhere in the world to this Linux machine that we are about to create. Once this is confirmed, we'll check and launch our machine. We are on AMI Linux 2. We are on T2 Micro with 1 vCPU and 1 GB of memory. The SSH port is also open. All the information that is on your screen is correct, so you can now launch the instance. On Amazon Web Services, the Linux machines are secured and you can only connect to them by SSH using a key and not a password. You can either choose a key pair or create a new one. Today we'll create a new one. Choose the name you like. I'll call mine my first instance. You have to download it, but only once. Once saved, a file in PME format appears, which is the standard format for SSH keys. We then launch our instance. You'll see a message indicating that it is starting. Let's now display the running instances. You can see here my first instance in T2 Micro, which is running. When the indicator is green, it means that the machine is operating. If you haven't selected a free machine, well, this will generate fees. Regarding the behavior of the machines, how do we turn it on and how do we turn it off? We can apply several actions. We select the Action tab. In the Instance Status subsection, we can either stop it, restart it, or terminate it. If we shut down the machine or restart it, it will keep all the settings that have been applied and the stored data. However, the termination will result in a termination of the storage and the instance. Today, we have created our first instance. We'll see later on how an IP address or other parameters can be modified. Now that we have created our first instance, let's see how we can connect to it. So based on the operating system you have, whether it's Linux, Mac, Windows, version prior to Windows 10 or Windows 10 and above, you have the ability to use SSH. On Linux and Mac, this functionality exists from the outset. It does not exist on version lower than Windows 10, and on Windows 10 and above, it is clearly superior. It is even possible to make SSH. In the case that you can't make SSH, it is possible to use a tool called Qu'est, which can be used on earlier versions of Windows 10 and on newer versions. In case that you can't use either SSH or Qu'est, there is a tool called EC2 Instance that allows you to connect to your instances through the browser from any operating system. We have made 4 tutorials to explain you how to connect with these different tools. One for Linux and Mac, one for Windows 10, one for Qu'est, and finally one for EC2 Instance Connect. To know which procedure to follow to connect to your instance, if you are on Mac or Linux, I invite you to look at the SSH tutorial for these platforms. If you are on Windows, I invite you to look at this same procedure. Mostly to understand the notion of chmod 400, which is the notion regarding the rights on the files of key. If you have a version prior to Windows 10, I invite you to watch the video on how to use Qu'est. And for those that have a version newer than Windows 10, I still invite you to watch this video. To all users, I recommend to watch the video regarding EC2 Instance Connect. If your application one day doesn't work, you can always rely on this tool to connect to your instance. SSH is often a complex principle, so if you encounter some problems and you can't get it to work, you should watch the video once more. Very often, students tend to miss a few elements. If you still are struggling, well, you should read the troubleshooting guide on SSH that is provided with this course. And if you can't find a solution and that you're still struggling, you can still use EC2 Instant Connect. Now that we have created our instance, we'll see how we can connect to it from a Linux or Mac system. Our machine relies on AWS. It's a Linux machine with a public IP address. The port 22 is open to users thanks to the security group. This port 22 will allow us to communicate with the machine thanks to SSH. It's the most important tool when using an EC2 machine. So this will allow us to connect remotely to this machine and administer them with command lines from our computer through the internet. Today we will see how to connect to our instance with our Linux terminal. To connect, we will go back to our instance, we'll find our DNS information, our public IP address, which we'll copy and use to have access to our machine. Go immediately into your terminal. To have access to your machine, you need to type the following command: ssh ac2-user at the IP address of your server. As you connect, you'll be able to find your machine. You'll then be asked to confirm the connection to this unknown machine. Enter yes. A message appears saying permission denied. This is normal since we do not want anyone to connect, and well, that's why we have a key pair. The keys will be used to authenticate yourself to your EC2 machine. Quick reminder, you have downloaded your key. Mine is called My First Instance. It is in PEM format. To connect to your machine, you need to tell SSH to use the key. To do so, type in SSH-I, your key file, EC2-user at the IP address of your machine. You can see what I've typed, just make sure to put the right IP address and key file. Then press enter. You're now in your machine. And you can issue new commands, for example, who am I, which will return the name of the current user. Or we can even ping Google. And as you can see, you have an answer. To exit, you have to type exit or Ctrl-D. That's it. You've learned how to connect to your machine when using Linux or Mac. In this lesson, we'll learn how to connect to our Linux instance from a Windows software while using SSH. Our Linux EC2 machine runs on AWS. It has a public IP address, and if you remember, we have set a security group that allows us to communicate with this machine from the port 22. SSH is the most important tool for connecting to our machines, as it allows us to take control remotely and execute commands. To do this, you'll need to install or use SSH from your personal computer. You'll be able to communicate through the internet. Today we'll learn how to configure our computer to connect to our instance with the free PuTTY software available online. We'll download it, install it, and configure it. First, let's search for the PuTTY software on the internet. Go directly to the organization website and download PuTTY. As you click on the website, you see that you have different options regarding the different versions. I'll install the 64-byte version. Save it and install it by default. Once that is done, we can now import the key that we downloaded earlier when we created our instance. To do so, go and get the PuTTY folder and open PuTTY-gens. This software will allow us to import the key. We click on File, then on Load Private Key. and we'll then be able to retrieve our key in our system. I've put mine in the download folder and more precisely in the share folder. To make the key appear, you have to select at the bottom right, display all files. My key file named My First Instance in PEM format appears. You can then select the file. Putigen informs us that the file was well imported, but that in order to use it, it is necessary to save it. We save our putty key. Putigen displays a message asking if we want to save this key without adding a password to protect it. In my case, I select the option yes because I do not want to type a password when I connect to the machine. It simplifies the process. Although the key will be saved under the same name and that it will appear by the same name, it will have a different format. This time it will be in GPK. Now that our key in PM format has been converted to the TEK format, it can be used with PuTTY to connect to our machine for the first time. With PuTTY, we want to connect to the IP address of our server. To do so, we'll go back to the console and get the IP address of our machine, which we'll copy. Return to PuTTY and paste it directly here. In SSH, there is a concept of user at the time of the connection. Therefore, we'll add the EC2 user set by default. To do so, type EC2-user at our IP address. We will now be able to save our profile named My First Instance. Once done, we can test the connection. An error message appears notifying us that there was no supported authentication methods. This is due to the fact that we didn't associate our GPK key with our profile. So let's take care of that right away. To associate the key to the profile, you have to open PuTTY again. We'll first load the profile and then go to the Connection tab. Select SSH and then Auth, which stands for authentication. We'll be able to define a file of authentication for this profile. We'll go and get the key from the folder. Take the key in the TPK format, go back to the session and save it. To make sure that the modification have been applied, try to connect again. As you can see, we are well connected to the Amazon Linux EC2 machine with the EC2 user. Since we are now in our machine, we can launch some commands. Who am I, for example? It will show our logging identity, here EC2 user. By typing ID, you get all the information regarding the system. Lastly, we can also ping the outside. We'll make a test on Google, which as you can see works. To exit, we can type exit or Ctrl D To check that our profile is working properly, we'll make a new connection with PuTTY. We'll load our profile again and open the application once more. As you can see, it properly works. So you've seen today that we can easily access our EC2 console with a Windows machine. In this lesson, we'll learn how to connect to our instance through Windows 10. We have our Linux EC2 machine on AWS with a public IP address, and remember, there is a security group that allows us to communicate with this machine from the port 22. SSH is the most important tool for connecting to our machine, as it allows us to take control remotely and execute commands, all while having a secure connection. We connect through SSH from our PC and we contact our machine by using the internet. Today we'll see how to configure PowerShell and the command line to connect to our EC2 machine. On the latest version of Windows, in the command line, we can test the SSH command. We then get a return which indicates the command actually exists. In the same way, we can test the same SSH command in the CMD. And we do actually get a return. The correct functioning of this command guarantees us that the SSH is installed on our machine. If you ever find that this command does not exist on your computer, then I invite you to look at the procedure for using SSH with PuTTY. So to connect, we'll take the parameters of this command line and type in SSH-I. -I will tell us the path to our certificate. My file is here. I right click on it, I select property and copy the path of the file. Using the tabulation, select my certificate in PM format. Now that we have our certificate, we will indicate to our command line the IP address of our server as well as the user to connect to. To do this, we'll go back to our instance and we'll copy the IP address in the clipboard. For this type of instance, the default user is the EC2 one. So we'll go back to our command line and type in EC2 user at the IP address of our server. We press enter and we can connect. Windows asks us if we want to continue this connection since it is the first one. I simply type yes, and as you can see, a message appears telling us that our key is not protected and therefore we can't continue the connection. If you have watched the video on the installation of SSH with Linux&Mac, for recall, we use the command chmod to modify the rights of our key so that it is accepted during the connection. It is the same system, however, This time under Windows, we'll manage the problem differently. Although we cannot launch this command, we will try the chmod. The chmod does not exist on the system, so we'll go through the file system. That way we'll be able to modify the properties of our file so that it complies with the standard in terms of security. We will go to security, then to my account. There are indeed some rights protecting our file. We will modify those by clicking here on ownership of the file. If you are not the owner, you need to do the following commands. First, appropriate it, check it, and finally validate it. Now we are going to delete the other users, the administrators. As you see, those users can't be deleted because they are rights that are inherited from the system. We'll disable the inheritance and convert the inherited permissions to explicit permissions. So once this is done, we'll be able to delete the administrators, the system, the authenticated user, and all the users of my machine. I check the properties in terms of security. I am the only user who has the right to this file. We'll then modify the permission on the file to have total control. Once done, we'll be able to test our SSH connection again. We write the command, and this time we are connected to a machine on Amazon Web Service using SSH on Windows 10, thanks to PowerShell. Let's test it again with EC2. We type in the command and it works correctly. So today we have seen how to connect to our EC2 machine from Windows with the command line and with PowerShell. Let's assume that you can't connect either with SSH or with PuTTY or with any of the tools we have seen before. There still is a possibility to connect to the instance by using the console. We click on Connect, several solutions appear. The first one is an autonomous SSH client. The second one is a session manager. We will come back to this method later on. Finally, you have the ability to connect by using EC2 Instance Connect. Today we'll be using this very last method. The process is rather simple. We connect with the default user of the Amazon image we have chosen, in our case the Amazon Linux 2. We are then connected to our machine. With this method, there is no need to manage a key, In the background, the console will generate a key on the fly and for this session only. These are temporary keys that ensure a secured connection. So it is possible to apply the same commands. By typing "who am I," we get the same answer as with the terminal in PuTTY, but here the process is simplified and therefore much faster. Here everything is done from the browser. EC2 Instant Connect is rather simple to use. That's it for today. In this model, we'll discover how security groups work. This will be a general overview to get the basics down. Security groups are essential to protect the network on AWS. In a general way, security groups allow to manage the incoming and the outgoing traffic to our AWS resources. To put it more simply, we have different elements. Our EC2 Linux machine, the outside world represented by the web, and in between we have our security group, which allows us to manage incoming and outgoing traffic. Having knowledge regarding the security groups is essential in order to be able to diagnose and solve network problems on AWS. In this model, we'll learn how to open and close ports. Although it may seem that network problems are necessarily related to security groups, we'll see that sometimes they might not. So now let's go to the console. Here on the information of our Linux machine, we have our security group. We'll display the incoming rules. We have the port 22 open. Let's first check that we can connect by using this port. To do so, we'll go back to the terminal we used before and connect. As you see, it works correctly. So this means that we can now modify the security group. We display the security group, a description appears, including the name and the ID. We have the incoming traffic, authorized when using SSH on the port 22 in IPv4 and IPv6. And regarding the outgoing traffic, our machine can communicate with the world freely. Let's say we delete these rules. To do so, we click on Modify, we delete the SSH rules and save the changes. I then return to the terminal and try to connect again. You can notice a very long waiting time. After a given period, a timeout message appears. This means that the SSH protocols has set a time limit beyond which an error message is displayed. I abort the command since it won't work. This is due to the lack of rules when it comes to the outgoing traffic that tries to connect to our EC2 machine. So we'll create a rule. Here we have a drop-down menu that allows us to choose several models. In our case, we are interested in doing SSH in TCP on port 22. Now regarding the choice of the addresses which can contact us, if I choose the option My Personal IP, it will only be possible to connect when using my own home IP address. On the other hand, if I choose the option From Anywhere, I will be able to connect from anywhere in the world. So we'll choose the option from anywhere just to make things easier. In the description, you can type in SSH to my EC2. We can now save the changes, and we do have our role in IPv4 and IPv6. We return to our terminal, we restart the command, and it actually works. So that's it for the basics of security group. Let's now look in more details at how a security group works. As we've seen previously, security groups act like a firewall. They allow us to manage access to the ports of our instances. Those security groups define which IP addresses are allowed to connect to our instances, either in IPv4 or in IPv6. It allows us to manage the incoming and outgoing traffic. This information is presented in a table highlighting the type, the protocol, the port ranges, and a source and description. Here is a diagram of how the security group works. We can see the distinction between incoming and outgoing traffic to our EC2 instance. Let's take the example of our personal computer. Its IP address is authorized to communicate with our instance on the port 22. When we try to connect from a computer authorized by the security group 1 using SSH, we manage to connect to our EC2 instance. However, if we try to connect to the same instance, but this time with a different computer, not authorized, to connect to our instance, thanks to the security group, our EC2 will never receive the requests from this computer since they are filtered. Our EC2 instance can freely communicate with the outside world because all the outgoing traffic is allowed. It is important to know that security groups are not linked to a single instance. We can assign a security group to several instances, several resources. A security group applies to a region. We have already seen the notion of regionality of some services, and while the security groups can also only apply to a single region or to a VPC. Security groups exist independently of EC2. This means that when traffic is blocked by our security group, our instance is not informed at any time. It is easier to maintain and manage when having a separate group for the SSH, in which can be added other groups and users in order to have a more organized management of connections to your resources. Let's say you have a problem connecting to your EC2, and at no point you are able to connect to your machine. This is most likely due to a problem related to a security group, ports that may not be open or settings that do not provide sufficient security. If you're able to connect to the machine, but however the response does not correspond to its determined performance, what's happening is that you're getting through the security group to contact your EC2, but you're facing a problem that is related to your application or the machine settings. By default, all incoming traffic is blocked and all outgoing traffic is allowed. We will therefore see a case where it is possible to include a security group in another security group. This can be interesting since it allows users to avoid redundancy. You can create several security accounts. Let's say that our EC2 instance has a first security group that authorizes incoming traffic for group 1 and 2. You also have another machine, an EC2 instance, that is linked to the group 2. When connecting to our left instance, it will work since the group 2 is authorized by the first security group. If we check a second instance, which this time is linked to the first group, it will also be able to connect to our EC2 instance. Now, if we check an instance that is linked to the group 3, which is not authorized by our security group, it will obviously not be able to connect. That's it for our course on security groups. In this video, we'll make a recall on the network, but also on the private and elastic IP of AWS. There are two types of IP address: IPv4 addresses, which are expressed in the form 1, 2, 3, and 4, and IPv6 addresses, which are expressed in hexadecimal composed of numbers and letters. In this course, we'll only use IPv4 addresses as they are the most commonly used by businesses and individuals. The more recent IPv6 meets the needs of connected objects. IPv4 addresses offer more than 3.7 billion attributable public addresses and is expressed in the following form: 4 bytes ranging from 0 to 255. Quick reminder on the network. Let's imagine we have a first public web server, A, with a public address. This one will connect to the web thanks to its public IP. We also have a second server with a public IP address who will also connect to the web. It will be able to communicate with the public address of the other server by using internet. We then have here an organization with a public address corresponding to its router or proxy, and a local network on which the machines of the local network can communicate. We have a second company with the same public IP address and private IP addresses within the network. In order for the two organizations to be able to communicate on their private network, they will have to use a VPN. Otherwise, there will be a routing that will be done through the routers. You might wonder what are the differences between public and private addresses. A public address is reachable from the outside world. It is unique on the web and cannot be assigned to mobile machines and can be easily geolocated. The private address is only reachable within the private network or through a VPN. It cannot be assigned to multiple machines in the private network, but the same IP address can be assigned in different private networks. The machine in the local network connects to the outside world via a proxy or a router. Only the specific IP addresses, ranges of each class A, B, and C, can be assigned to public networks. When stopping a machine on AWS, the address changes systematically. If you want to keep the same public IP address, you need an elastic IP address. The elastic IP address is an IP that you own, that you reserve. It is a paid service. It can only be assigned to one machine at a time. And therefore, with an elastic IP address, we can compensate for the failure of an instance by quickly relocating the IP address that we have reserved. You can only have 5 elastic IP addresses at once. Beyond that, it is necessary to look at the AWS price list. Having confidence in the DNS technology, it is strongly advised to not use elastic IP addresses. The assignment of a fixed IP address may reflect poor architectural decisions. It is better to buy a domain name and associate the name of our instance with it. The name of the instance does not change thanks to the DNS management by R53. We can also define unique entry points to our platform. By setting up load balancers, this allows us to direct the traffic. By default, our EC2 instances have a private address to communicate with each other on AWS, a public address to reach them from outside. If we want to connect to our instances via SSH, we can only reach them by using their public IP, and conversely, we cannot reach them by using their private address, except when using a VPN. If your instance is stopped unless you have an elastic IP address, its public IP address will change. So let's go back to the console to check on our instance. At the moment it is stopped. We can see here that there are no IPv4 and IPv6 and elastic addresses assigned. When we start the machine, you have to wait, of course, a few seconds. However, once launched, you can notice the appearance of an IP address. As you can see here, it begins with 35. We'll be able to test the connection in SSH. You can see that the address I have here is different from the one I have after rebooting my machine. To connect to your instance, you have to pass the new address. Since this is our first connection with the new address, the machine asks us to confirm the connection. Once you've confirmed, you can see that you're well connected. If I switch it off again, we can see that the machine keeps its private address, but that the public one has disappeared. It will be renewed at the next startup. Let's restart our machine. We'll assign it an elastic IP address in order to have a fixed address for our EC2. To do so, go directly in the menu, Elastic IP Address. We click on Allocate a new address. We choose the IPv4 address option from the Amazon pool. If you already have your own Elastic IP address, you can select the second option. When clicking on Allocate a new Elastic IP address, it is directly allocated to us. We close the tab. Now we have to associate this IP to our instance. To do so, select the option Associate the address. This address will be used for an instance. You select the one of your choice. It is not necessary to change the private IP address. Once you have completed the steps, you can associate it to the machine. Now let's go back to our instance. We can see that the IPv4 address corresponds to the elastic IP address. The private address is identical to the previous one. Let's reconnect by SSH on the machine with the new IP address. Be careful to replace the address. Very often we tend to forget it. And you see that you're now connected to the EC2 machine. As you can see, we keep our IP address contrary to what we saw at the beginning of the course. If you want to disable the elastic IP address, because this service is not free, you have to dissociate it. You must know that just by having an elastic IP address in your menu, it will generate costs. It's really important to get rid of these addresses. So I'll be releasing the address and going back to the instance. In this lesson, we'll be installing the Apache web server on our instance. To do this, we'll connect via SSH. We'll launch our console with the new IP address that has been assigned to us. As usual, we'll validate. The first thing we have to do is to type in the command that you see on the screen. It will allow us to modify the rights in order to install the Apache web server. We will update the system by typing yum update -y. It will allow us to have the latest version available on our system. Now that our system is up to date, we will clean the screen and install Apache. We then type in the command install https -y. The -y will allow us to not answer the installation questions. Now that the server is installed, we'll start it. To do so, you have to type in a new command, systemctl start httpd.service. As you can see, the service has started. For it to start automatically, we'll activate Apache on our system. To do so, type in the command systemctl enable httpd.service. Now to check that our system works properly, type in curl localhost 2.18. We then find ourselves with a page full of lines that's quite difficult to read. In order to console the same page on the web, we get the public address of our instance and we simply paste it on the browser on the port 80. As you can see, this takes a little time, and as we have already seen previously, it can potentially lead to a timeout. Let's check this out. We go to our security group, and here we see that only the port 22 is allowed on our instance. To be able to access our web page and server, we'll modify the group, and in the incoming rules, we'll add a new one. We already have a rule model for HTTP on port 18, so we indicate role by typing in the name of our service, apache. Once you've done it, save the changes. Returning to the page, you'll see that the test page will indicate us that it is being used for the installation of apache. It's meant to allow us to verify the installation of the service. Similarly, the web page informs us of the need to add content to the following element. I empty my screen. We create an indexed page for HTML. In which there will be a basic message, hello everyone, and we have to send this message to the command /var/www/html/index.html. Once you've confirmed the command, you can go back to your page and refresh it, and you'll see the message that you've put in place. As you can see, I've made a small error. To correct it, go back to the control center. I'll remove the extra word, and I'll confirm again. So we've managed to display our first web page. In order to make things more interesting, we'll modify this page and add a new message. For example, hello everyone, I am the server, and then add a variable. As you refresh the page, you'll see the new message, followed by the private IP address and the zone of our server. So today we have made our first personalized HTML page. In this lesson, we'll learn about EC2 user data. It is possible to personalize our instance during the installation by using user data scripts. In reality, the process is quite easy. It's just executing commands when the instance gets installed. User data scripts are used to perform tasks such as installing updates, installing softwares, retrieving content from the internet. That is to say, most of the things that can come up to your mind. These scripts run on the instance with the rights from the root account. In this lab, we'll deploy our instance, making sure that Apache is installed on it and that our home page is personalized. The script that we will add on will run as we launch our instance for the first time. So first, we'll go back to the console and resign our first instance. While this one is being resigned, we'll be able to launch a new instance. Obviously, we'll select the offers eligible with the free formula. We stay on the T2 micro. The parameters do not need to be modified. What really matters to us is the advanced details section. So we'll go to the user data section. This is where we can add our script in the form of a text. I have already created a script. You must know that the first command is always the same and must be present. What we are about to do will enable the automatic activation of the commands that we have added one by one during the previous video. To do so, we add the following lines. Our server will be updated, our service will be installed and started, and a custom page will be added to our server. Once that's done, we can confirm. Storage and tags have to remain by default. Concerning the choice of the group, we select the one of my first instance in order to authorize the traffic on the port 80 and on the port 22. To verify that everything is working correctly, we launch, select the existing key and click on Display Instances. As you can see, our instance is now starting. Once it is launched, we can check that our script has worked. We will type in the public IP address of our server and we'll get the desired message with the same information as in the previous lesson. In the same way, we can check that our SSH connection is still functioning. To do this, we go back to Windows PowerShell. We then start an SSH connection to our new public IP. The connection is established. We can then display the contents of our HTML index file. The desired message then appears. That's it for the user data script. As we've seen, it allows the automatic installation and deployment task of our instance. In this lesson, we'll discover all the different types of instances. we will look at the on-demand instances with a low workload or the reserved instances that require a 1-year subscription. This category is divided in several subcategories. On the one hand, you have the reserved instances for long activities, and on the other hand, you have the reserved convertible instances, useful for a more flexible use. They allow to modify the instances during the use, contrary to the reserved instances, where it is only possible to use a unique and same type of instance. Then there are the scheduled reserved instances. The machines are then started up according to a specific time slot. Moreover, you have spot instances useful for more shorter activities. These are inexpensive, but it's possible to lose the instance. They are less reliable than the classic instances. There are also dedicated instances. For these, the server is unique to the company. It is not shared with anyone else. Finally, you have also the ability to contract dedicated hosts. They allow to reserve a whole physical server. It offers the possibility to control the placement of all the instances. These instances are useful when operating an Oracle database. They allow to have a visual on the processors and other elements. Let's move on to the on-demand instances, for which we only pay for the use of our instance. The billing starts after the first minute and is billed per second. These are certainly more expensive, but there is no subscription cost. On-demand instances are without commitment and can be cancelled at any time. They are recommended for short or uninterrupted workloads, meaning when it is not possible to predict the behavior of an application or a service. Then there are the on-demand instances, which are more in line with IT usage. These can be up to 75% cheaper than the on-demand instances. It is necessary to pay an amount in advance for the future use of the instance with a minimum duration of 1 year. So this duration is flexible. It can go from 1 year to 3 years. Moreover, reserved instances are specific to a type of instance, so it is impossible to modify them during the use. These instances are ideal for applications with little evolution, like database servers. If you're looking forward to create a database server for 3 years, this type of instance is highly recommended. Convertible reserved instances are of the same type as the classic reserved instances, but it is possible to change the type of instance during the use. This manifests itself by the possibility of modifying a large C4 by a large C5, following a load increase or the implementation of new prerequisites. Then we have the planned reserved instances. They allow to plan the launch of an instance at a defined period. If we take the example of a database server, it is possible to select a period from 3 days to a week or even to a month. This type of instance allows to create a periodicity and thus to use the resources only when needed. Then we have the spot instances. They allow up to 90% of savings compared to a classic on-demand instance. However, these instances can be lost according to supply and demand. If the maximum price you invest is lower than the market price, the instance will be awarded to the highest bidder. For example, if you want to pay $10 for your spot instance per week, then when you apply for a spot instance and it is allocated to you, it is possible they will be allocated to someone else if the amount offered is higher than yours. Nevertheless, this type of offer ensures the best value for money on AWS. The price difference is over 80%. Spot instances are ideal for fault-tolerant users, such as script execution and data analysis. Since those are one-time tasks, in case that the mission stops, they can be restarted quite quickly. Spot instances are not suitable for large workloads or long period of times, since the instance can be lost. For example, if you're using a spot instance as a database, it's even possible to lose the contained data. A good combination would be to have dedicated instances acting as databases and on-demand instances for more occasional tasks. Now let's take a look at dedicated EC2 hosts. They are meant for personal use. They allow you to have full control over the placement of the instances. You even have the possibility to see the hardware and the core of the server. This type of instance is useful when the user has to manage a lot of licenses. The creator has an eye on the number of processors. This type of instance can only be linked to the account of the creator and for a period exceeding a year. It allows the creator to define a price adapted to the licenses, but on the other hand, this type of instance is more expensive. Dedicated EC2 hosts are ideal for applications with complex licensing models, but also if the company's security policy prohibits sharing server with third parties, or if compatibility needs are important. Dedicated instances run on a hardware that is reserved to you, so it is possible to share hardware on the same AWS account. However, it is impossible to move the instance to other zones. For that, you have to stop it first. The following table shows the different characteristics between dedicated instances and dedicated hosts. In general, we can see that a dedicated host is much more interesting and offers more services. But how do you make your choice? Choose an on-demand instance if your needs are punctual. However, you must be ready to pay a lot of money. A reserve instance can be selected if the use exceeds a year. Spot instances are useful for punctual needs. However, there is a risk of losing the instances because of the price on the market. We select a dedicated host if the needs of our activity require the rental of a physical server. Here you have a price list of the different type of hosts. As you can see, on-demand host will cost 10 cents, while a spot instance is much cheaper than other instances. Reserve instances cost on average more than 6 cents. The price decreases if an advance payment is made. A 36-month reserve instance will cost almost 4 cents. The price changes again if you pay in advance. You should be aware that by choosing a different type of instance, there is the possibility to make different type of savings from 10% to 90%. We will now look at spot instance requests. As we saw earlier, spot instance allow us to have up to 90% reduction compared to a non-demand instance. The concept is the following. We define a maximum price that we are prepared to pay for a spot instance, and if the price we have defined is higher than the spot rate for our instance, we keep it. This is linked to the fact that spot instances vary according to the offer and the capacity of AWS. So if the price of your spot instance exceeds the maximum amount you have defined, there are two solutions. Either we stop our instance ourselves or it will be taken away. We have the possibility to perform this task for 2 minutes after our maximum price has fallen below the spot price. Another strategy to avoid losing your spot resources is to use what's called spot blocks. These guarantees the availability of the instance for 1 to 6 hours without interruption. In some cases, the instance can get stopped, however, it can be recovered. But this happens very rarely and is not written on paper or in the AWS FAQ. This type of instance is suitable for one-off tasks such as data analysis, that is to say, failure-tolerant tasks. Generally speaking, you don't do database with your instances. It would be too adventurous. Spot instances are therefore not suitable for critical tasks and for database servers. Here you have an example of the spot instance prices. So on this table, we have chosen the Linux product with an instance type M4, large, for a duration of 3 months. We have defined a maximum rate that we are willing to pay in relation to different zones. So if we take this line and if we choose, for example, US East 1F here in gold, we see that when we subscribe, these spot instances are more or less aligned with my maximum price. However, here the maximum price of my spot instance is above than what I'm willing to pay. In that case, there is a risk of having the spot instance interrupted. Here, on the other hand, I can keep my spot instance. That is to say, start it and use it. On the other hand, you can see that here the prices are relatively aligned. There are no major changes except here for US East 1C. You also have the on-demand prices, and we can see that we are really well below the cost of an on-demand instance. We'll now see how to switch off a spot instance. To turn it off, we need to understand how a spot instance creation request works. We are going to make our request, we are going to express a maximum price, we are going to indicate the number of instances we want, as well as the specificities of the launch. We can launch an instance once, in which case our spot request will be deleted when we create the instance. Since this is our case, when we make our request, we have to define the specificities of our instance and its validity period. The instance is launched once and our request is deleted here. The other mode of launching is the person mode. So we'll make a person request, our instance will be launched, we'll be able to stop it, restart it, interrupt it. But we'll always have our spot instance requests, which will exist in our spot instance console. This means that if your spot instances here are turned off for the person mode, and if your spot instance request is still active and existing, then it will find itself a way to restart your instances when your maximum price has gone down below or if your instances have been turned off by accident. So now, in order to stop your spot instances, our request has to be open, active, or deactivated. We don't need our spot instance request to be closed or cancelled or failed. And so this also means that we can only stop an instance in these three cases. The instance can be cancelled, however, it doesn't mean that it will be terminated. In order to cancel the spot instances, we have to be in the case where our request has been validated until the end. Then we have to delete our request before we can delete our spot instances. There are also spot fleets. The spot fleets correspond to spot instances and instances on demand, but this can be optional. The fleet will try to reach the required capacity according to the defined rate, according to our maximum price. We can define pools of instances, the type of instances, the OS, the availability zone, the regions for each of our spot instances. We'll also be able to define several pools so that our fleet can choose which fleet to launch in order to best fit our requirements in terms of price and number of instances. Fleets can stop and start instances if the defined capacity is reached or if the maximum price is exceeded. The strategies to allocate the spot instances are the lowest price strategy. From the cheapest pool, we'll optimize the cost, which will imply a low workload. We also have a diversification strategy. Our fleet will draw from all the pools that we have defined to get the best value for money and according to the resource available. Which will enable us to work on high availability and large workloads. We also have the capacity optimization, meaning that our fleet will choose the pool with the best capacity in relation to the number of instances required. And finally, the fleets allow us to automatically request instances at the best prices, which is very valuable in terms of saving and costs. So we are now going to take a look at what we saw in the previous lesson. As we go back to the instances, here, if we try to launch it, a non-domain instance will be launched. We are going to take a look at reserved instances. When buying a reserved instance, the type of instance needs to be defined here. Let's take something that has a significant cost, such as an M5 large, with a duration of 12 to 36 months. Several proposals appear. Some are more or less expensive. The initial price is 0. We'll take this offer as it is more meaningful for our example. When buying 4 of these machines, the price that needs to be paid equals $2,440. That's just the cost of the subscription, and then we'll have the consumption. The hourly rate is set at $0.023 per hour. Of course, we won't confirm our purchase as it is way too expensive. The next type of instance that we will see are the scheduled instances. Be careful if, for example, I go to Paris. We'll see here that the scheduled instances are not available in all regions. So we'll go, for example, to Northern Virginia, and we're going to be able to make our request for a planned instance. We are going to buy a scheduled instance, and we have several pieces of information here, such as the start date of our instance. We can plan the creation of our instance at more or less 2 hours from 9 p.m. on August 3rd for a duration of, let's say, 24 hours. We may have a treatment that will last for 24 hours with a weekly recurrence, and let's say on Sunday. So now we have to make a few choices. Regarding the type of instance, we choose Linux. The availability zone, it doesn't really matter. And for the type of instance, we'll select a C3 large. As we can see, there are no products that match our search, but the idea was mainly to see how you can plan the start of your instance, define the running time, that is to say the recurrence, whether it's weekly, daily, or monthly. We can choose the type of instance as well. So now you know how to make a scheduled instance request. Let's go back to Paris. Here we can see that for this service, the regions supported for scheduled instances are Northern Virginia, Ireland, and Oregon. Let's go back to EC2. We'll now look at dedicated hosts. As I explained earlier, those will allow you to keep licensing costs down as you use the license you already have through the BYOL, bring your own license model. This makes it easier for you to meet the compliance and regulatory requirements that apply to your business. To do this, we click on Add Host. We're going to choose the instance family M5D, the instance type M5D.large, the region EU West 3A, and once that's done, we can click on Allocate Host, and that's going to create our host directly. In my case, I'm not going to click on it, as it's a paid service. I'm going to go back to my console. Let's take a look at spot requests. As we saw earlier, the spot requests allow us to automatically deploy our spot instances. So for example, here we can have a history of the pricing. We can choose the type of instance, the periodicity. It can be set on a week, on a month, and we can know the price in real time of the instances. It seems to be very stable, but don't forget that if ever your maximum price exceeds 3 cents, Amazon will be able to recover the spot instances that you have allocated. So be very careful with that. So we can create our punctual instances, our spot instances. We can define the type of workloads that we want to use, load balancing workloads, flexible workloads, big data workloads, or defined duration workloads. So we can be sure that our instance will not be recalled by Amazon between 1 and 6 hours, as we said earlier. For this example, we'll choose load balancing. We can choose the type of instance, the VPC, the availability zone. We define the key pairs that we will use, the number of instances, or the number of vCPUs that we need. We will be able to choose if we want to maintain the target capacity, so our spot instance will always try to get us to our capacity and instance requirements. So here we have a small summary with our fleet, which will be composed of certain numbers of machines. So we can also define whether or not we want to follow Amazon recommendations. Then on the fleet allocation strategies, we have the optimized capacity, as we saw earlier, the diversified strategy, disrupted among several groups of instances of my fleet, or the lowest price, so the cheapest price strategy. After that appears a summary with the hourly rate and the number of savings I make in relation to my request. You can click on launch, but again, I'm not going to do that because it's obviously not free. So let's go back to the EC2 console. This is how you launch a fleet. To launch a spot instance by itself, we'll go to Instances and click on Launch an Instance. We will choose our Amazon Linux 2 image in T2 Micro. And so here we'll say that we want a spot instance. And so in relation to the availability zones, we'll have a price estimate of what our instance could cost us per hour. So we are always well below 10 cents for the on-demand instance. Here we'll be able to indicate the maximum price, so I will say $10. That's even too much because we saw that an instance would only cost 10 cents, so you need to put in 11 cents. Is our demand persistent? And what is the behavior to adopt when our machine is stopped? So either we shut it down, or we terminate it, or put it into hibernation. We can define the validity date, the VPC. So really a lot of options in relation to the creation of our Spot instance machine. We can put nothing if we intend to use it for a very long time. We can define the number of Spot instances. Then the procedure to create your Spot instance is exactly the same as to create a on-demand instance. So you know more or less the different types of instances, how to launch them, how to create a Spot, a dedicated, a scheduled and on-demand instance, and a fleet of Spot instances. In this lesson, we'll see different types of EC2 instances. As your instances got created, you might have noticed that the name was composed of a letter, such as P2, C5, M5, etc. These letters have a meaning, and in this lesson we'll discover the most important ones. So first off, we have the instances starting with the letter R. They are intended for applications that need RAM, hence the letter R, as well as cache memory. Instances that start with the letter C are applications that need CPU and will be adapted for computing or database management. Machines starting with the letter M for medium are applications that are balanced between RAM and CPU, and therefore these instances will be better suited for classic applications or standard web application. The I stands for the application that need a good level of input and output in terms of writing to the hard disks, which can be interesting for instance storage as well as for databases. The letter G is for applications that require the GPU for video rendering or for machine learning. We have T2 and V3 for instances limited in processor expansion capacity. These are called burstable instances, and we have the unlimited T2 and T3, which have no limit on the capacity of processor performance. For more information, I invite you to visit this link. Let's move on to instances with scalable capacities. AWS uses the concept of scalable instances for its T2 and V3 instances. These instances have a decent CPU performance, but when the machine is scaled up, the CPU capacity can be expanded and the instance can have better performance. When this machine expands its capabilities, it consumes a burst expansion credit. And if all the credit is consumed, the performance of the instance becomes really poor. You can see here an extract from CloudWatch. We have set up a monitoring against the burst credit, as well as the average burst credit still in our possession. So we can see here a peak in processor activity, and on the other hand, we have a drop in our average burst credit. You can find information about the capacity to reload bus credits for each machine in the tables we saw earlier. We can see here that the more powerful the machine is, the more CPU credit points we will have. The T2 and T3 unlimited instances, which have existed since November 2017, allow us to exceed this capacity linked to our bus credit without any loss of quality in terms of the CPU. But it is a paid service, so as long as you are exceeding your credits, you will be paying. As this is a new service, I would urge you to be careful with its use, as it can generate charges if not monitored properly. But above all, the most important thing for certification is really to remember these different designations. So the R, the C, the M, the I, the G, and the T, these are going to be the instances on which we are most likely to have questions at the certification level. That's it for EC2 instance types. In this lesson, we'll find out what an AMI is. It stands for Amazon Machine Image. As we have seen, AWS offers several types of image or AMI, such as Ubuntu, Fedora, RHEL, Windows, and many other images. These images can be customized and launched using user data. What if we created our own custom image with precise specification? We could create a more advanced Linux 2 image that already has apache installed on the home page. If we do this, we'll have a custom image that we can use to create multiple instances. We can build images for both Linux and Windows. Having a custom image offers several advantages. It is possible to install packages in advance. The startup of the instance is much faster. Machines are created with pre-configured tools such as enterprise applications. And security is enhanced. Private cloud machines are monitored on a recurring basis. Custom images are updated over time, and it is even possible to configure a domain joined at instant creation. Application can be stored upstream to make deployments easier. For example, if you have 10 machines to deploy and they have crashed, well, if you have a custom image with pre-installed application, the restart will be much faster. Using a third-party image allows you to optimize an application, especially those related to data or application service. AMIs are region-specific, An AMI deployed in Paris cannot be used in Ohio. It's also possible to use a public AMI. That is to say, an image created by a third party. You can then benefit from their experience and expertise. It is possible to pay for the use of another image. These images are optimized by their own owner. They are easy to configure and use. What you need to understand is that by using the skills and expertise of others to create your own images, you need to pay a certain amount. All available AMIs can be found on the website of AWS. For example, our Amazon Linux 2 has no cost, but if we improve it, it is possible to sell our expertise to other users. You have to be very careful when using public AMI. Don't use images you don't trust. Some of them may carry malware or present security risk to your business. How much does an AMI cost? AMI are backed up on Amazon S3. This service is not free. It can be a burden for companies. For example, here are the rates for the US East 1 region. The first terabytes are charged at $0.023 per gigabyte per month. The next 450 terabytes are charged $0.022. These costs are certainly very low, but for a company with hundreds of AMIs, this is a significant cost. It is therefore very expensive to store custom AMIs, and it is better to delete them when they are no longer needed. In this lesson, we'll learn how to create an AMI from one of our instances. I choose my first instance. We copy the public IP address to connect to it in SSH. Once connected, I switch to the user. I update the system. I install my web server. Once the web server is installed, to make sure it works, I start it. As the service starts, we have to make sure that it will restart the next time it's used. To do so, we have to activate it. Once done, I'll create a custom home page that I'll save in HTML. To test the local operation of the machine, we'll do a localhost curl on the port 80. The idea is to create an image that already has our web server and our custom page. To do this, we'll check that our server is accessible from the web. We'll get the new IP address. As we connect, we find ourselves facing a timeout. This is normal given that the security group allows us to communicate only on the port 22. We then modify the rules and add a new one for HTTP. If we return to our browser and relaunch the page, the desired message appears. I have created my server and it has Apache installed and a custom message. As I explained to you, the idea is to create an image. For that, we'll return to our instance, make a right click. We choose create an image, which we'll call my first AMI. I write in the description image that installs and activates apache. One of the important elements is the hard disk. It is on this one that we will save our image. We then create our image. It appears as being in the process of being created. Now that the AMI has been created, when we click on it, several options appear. We can copy our AMI. As I explained earlier, we can't move AMI to another region, but we can copy it to another region. We can also set the permission on this image, either public or private. We can allow another AWS account to connect to it. So we'll launch our instance from this AMI. We select a T2 micro. We confirm. Regarding the security groups, we will select a security group that has been previously set. We then launch the instance with our key pair. Since it's being launched, we go back to our display panel. We can see that this one is starting. Now that it is installed, we can connect to it for its public address. The address you see here is the one of the first server with which we created the image. If we pass in the address, as you see, we have the desired message created from the image of one of the instances. And that's it for today. In this lesson, we'll see how to copy an AMI from one account to another. So it's perfectly possible to share an AMI that you have created with another user. Sharing this AMI does not affect the owner. If you share, you remain the owner. If we copy an AMI that has been shared with us, we own that AMI in our account. To copy an AMI that has been shared with us by another account, the rightful owner of the AMI must give us permission on the storage where the image is saved, whether it's on USB storage or S3 storage. So you might wonder, what are the limits to sharing AMIs? You cannot copy an encrypted AMI that has been shared with you. However, if the encryption key was shared with us with the AMI, we can copy the AMI with our own encryption key. Since we now own a copy, we can create an AMI from this instance. Similarly, we cannot copy an AMI associated with a paid product from another account. This includes Windows AMIs as well as AMI from AWS Store. To copy this type of AMI, you need to start an instance from the shared AMI and then create it from that instance. So now we'll see how it looks in the console. So here I have my AMI. On the console it appears, and if I want to allow someone to be able to run my instance, I'll put add permissions here. For example, for a normal user, I'll add and then I'll know that this user will be able to run my AMI. However, he will not be able to copy it. If I want the person to be able to copy my AMI, I'll click this box and it will give the appropriate permissions to the person with whom I'm sharing the AMI. I save. As we've seen, if the person wants to copy my AMI, they won't be able to copy it directly. They'll have to launch the AMI and then they'll be able to create an AMI from the instance they'll launch with my AMI. This is quite simple, but it is a concept that must be understood for the certification process. So in this lesson, we'll look at placement groups. From time to time, when we create our instances, we may need to put them on a certain availability zone in order to improve performance, or to guarantee high availability, or even to protect ourselves from failure. And so this kind or this type of policy can be defined in placement groups. Either you place your machines, or either you place the machines automatically in predefined zones, or automatically in a random fashion. And so when you create an instance, you have to specify one of the following three strategies. The first one is the cluster strategy. In this strategy, the instances are grouped in a low latency configuration on a single overlay zone, which guarantees high performance but also exposed to high risks. The second strategy, the spread strategy, consists of spreading our EC2s over different hardware and with a limit of 7 instances per availability zone for each placement group. This corresponds well to critical application, for example. The first strategy is a partition strategy, which is similar to propagation. However, the instances are distributed over partitions which are themselves distributed over different hardware within the same availability zone. This ensures high performance and very low risk. Finally, this type of placement group can include up to 100 instances. This corresponds to large applications such as Cassandra, Qu'est, or Hadoop. Let's take a closer look at the cluster placement group. Here we have our cluster placement group with our 6 EC2s. Remember that we can have up to 7 per zone. So we have our 6th instance on the same physical medium and on the same availability zone, which guarantees us low latency and very fast network traffic. The advantage is that the network is efficient between the instances. The disadvantages are that if the physical medium fails, all instances fail at the same time, in which case should you select this option. It can be used in big data for processing requiring fast execution and weekly jobs, for example, or application requiring low latency networks. Now let's look at spread groups. The spread placement group is the opposite of the cluster placement group because here what we want is to avoid that our machine can fail at the same time. So what we're going to do is we're going to put each of our EC2 instances on its own physical media in a given availability zone, which guarantees that if my machine 1 here, EC2 goes down, machine 2 will continue to work. If the all availability zone has a problem and stops working, I will have my application running on 2 other availability zones. What does this mean? What advantage does it have? We can spread our EC2s over several AZs, that is to say, availability zones. This reduces the risk of simultaneous failures. Our EC2 instances are on different physical media. The disadvantage is that we have a limit of 7 instances per availability zone. What are the use cases for this type of placement group? Application requiring very high availability and critical applications where each instance may be isolated from the failure of the others. Now let's look at paginated placement group. We are in the availability zone. We have our first partition with 4 EC2 instances, a second partition with 4 other EC2 instances. Remember that we can go up to 100 instances per partition, and the third partition with likewise 4 EC2 instances. This solution allows us up to 7 partitions and up to 100 instances per partition. The instance of a partition does not share the same physical media as the others. Finally, the failure of a partition can affect many instances, but will not affect the other partitions. To have access to the information regarding each partition, AWS metadata has to be used. What are the use cases? For HDFS, which are very resources-intensive applications, like HBAs, Cassandra, or Qu'est. Let's hear how to create placement groups in the AWS EC2 console. We'll go to Network and Security, Placement Group, and create our placement group, which we'll name High Availability. Next, we'll create a second placement group, this time from our critical application. And here we'll choose the spread mode. Once created, we'll create a third group. My disrupted application. This time I'm going to put it in a partition, and in terms of the number of partitions, as you can see right here, we can go up to 7 partitions. We'll start as in the example in the lesson, that is to say with 3 partitions, and we'll create our placement group in partitions. You can see here on the placement group console that we have our 3 ability groups, the corresponding strategies and the status, and there is the number of partitions where relevant. Now that we have created our group, we'll see how to assign them to an instance. Let's go to our EC2 console, we'll launch an instance. As usual, we use our standard T2 micro Linux2 AMI. Next, here in the options for creating your instance, you'll be able to choose the placement group. And by checking this little box, we'll be able to assign a placement group to our instance. We can either use an existing placement group or add a new one. What we'll do is use an existing investment group. We'll take the spread. You see you can only launch up to 7 more instances in this investment group. If I want to have the partition mode, I'll choose it here and I'll define the target partition in this drop-down menu where I'll choose an automatic spread if I want AWS to find the best solution to spread my instances. As you can see, there is no cluster mode here. This mode does not work for T2 instances, so what we're going to do is to go back to the choice of the instance and take a very large instance. An extra large M5A. So I'll do the following. Do I want to continue with this type of instance as it is a bit expensive? So I'll say yes for now. And so here I can choose my cluster placement group and I can create my instances in a placement group that guarantees them a very high availability. That's it. I'm not going to evaluate because I don't want to use a large M5A. However, this is how you assign placement groups to instances. In this lesson, we'll find out what an ANI or Elastic Network Interface is. This is a logical component of a VPC. It will act as a virtual private network card. Let's take the example of an availability zone. I have an EC2 instance here that has an ATH0 network card to which we'll attach a primary ENI that will allow us to provide our EC2 with connectivity through a private IP address. An ENI can have the following attributes: a primary private address, one or more secondary IPv4 addresses, For this example, one could easily add a second ETH1 card that would provide a second private IP address as a secondary ENI to be able to communicate with other instances or to be able to do failure over or load balancing. An ENI allows us to have one elastic IPv4 address per private address. It will also allow us to have one IPv4 elastic IP address per public address. We can also have a public IP address through an ENI. An ENI can belong to one or more security groups. It can also be assigned to a MAC address. There are other parameters and attributes, but these are the main ones, and we'll come back to the others later. It is possible to create an independent ENI and then assign it to an instance on the fly, which is ideal for failover. ENIs are linked to availability zones, so an ENI cannot be used in another availability zone than the one in which it was created. So for the example, we'll create a second machine with a first network card, and we'll create a scenario where the instance that communicates with its secondary ENI fails. We may have a machine here that does the same job, and so what we're going to do is we're going to reassign our secondary ENI to our second instance, which will allow us to quickly switch to a working server if our first instance is not working. Now we'll see in the console how this works. We are going to launch two instances quickly. So 2 in T2 micro. So those two machines will be set with default VPC. For the subnet, we'll take EU West 3A. Then I do the following: storage, tags, the safety group, we check and launch. Now our machines are being created. Here we can see interesting information. So we have a private IP address and a public IP address. We can also see that we are on our EU West 3 availability zone and our other machine is also here. What is also interesting is that we will find here in the network interface ETH0. So if we click on it, we see that our interface ETH0 is attached to the interface ID, so the ENI with this long string. So what happens if we click on our ENI? So we can see that we have our two machines, both have private and public IP addresses. If you want to access the network interfaces, you go to network here and network interface. You also have the possibility, as I did, to right click on this link. I'm going to remove the filter here, and so we can see that I have two ENIs, two network interface IDs that were created at the same time I created my machines. And if we move a little bit further, we can see that the status of our interfaces are in use with one public IP address each and two different private addresses because we have two different instances. The interesting thing about this interface is that you can create your own network interface. I will call it my ENI. The ability zone will remain the same. Here we can choose to automatically assign an IP address or define a custom IP address. The Elastic Fabric adapter is one of the elements of this interface that we'll see at the end of the training. You can also assign security groups. We'll take the security group we use to launch our virtual machine and create our ENI. So I remove the filter again. I can see that I have three ENIs, the one that we created when I created my machines, and the one that I created myself. Now we can attach our newly created ENI to one of our instances. So attach. We see that the status has changed to in use. Let's go back to our instances. We'll update. On our machine here, we can see that I have a first network interface linked to a first NIC, which will provide us with a private IP address and a second address, a second network card with a different IP address. From here, we can go back to our ENI. We'll say that our ENI here is going to be detached. So I'm going to detach it and I'm going to attach it. So it takes a few moments and then refresh. Now that my ENI is available again, I can attach it to my second instance. It takes a little while. I go back to my instances and I see here my first instance. So I refresh. My first instance has only one network interface left. My second instance has my second interface. Now if we go back to our ENI, we can manage the IP addresses associated with it. We'll be able to add and remove some. Which will be interesting. Then we can also change and assign additional security groups, for example. So this will allow us to have a greater security of our network connection of our ENI. What will be interesting for us and important for the training is to say that here we have a primary IP address. So a primary ENI that provides us with a private address, a secondary ENI that we can attach or detach to other instances. So a secondary ENI can be detached and a primary ENI cannot be detached from its instance. That's it for ENI. In this lesson, we'll look at the Hibernate service. Regarding the behavior of our instances, we know that we can stop or terminate them. When we stop them, all the data on our hard disk or on our AWS volume is kept and will be restored on the next restart. When we terminate, all the volume created at the launch of the instance are deleted. What happens when the machine starts up? On the first boot, the system starts, the user data script is executed, our application and all our services get installed. On the next startup, the system boots directly without the time it takes to install services and applications. And at this point, if your application takes a long time to load, or if it needs a lot of cache memory, and there are a lot of services associated with it, it can take even longer to boot your machine. AWS has introduced the Hibernate service. The Hibernate service is roughly equivalent to what you would consider a sleep mode. Everything that is loaded into RAM is preserved. This makes booting faster because the system is not stopped or restarted like a snapshot. How does it work? All RAM contents are stored at the root of your hard disk and your EBS volume as a file. This is why your EBS volume must be encrypted. Here is a little diagram to show you how it works. So we have our EC2 here running with all the information loaded into its RAM and volume. We are going to do a Hibernate stock, a standby of our machine. The hibernation phase corresponds to a RAM backup at the root of our AWS and the shutdown of the machine, the instance. In fact, we stop the instance, but we do not stop the operating system. So when we restart our instance, the system will be up and the RAM will be reloaded from our AWS. What is good to know about EC2 Hibernate? Not all instances type are supported. You can't do Hibernate on T2 or T3 for example. Only C3 to 5, M4 to 5 and R3 to 5 are supported for Hibernate mode. The RAM size must be less than 150 GB. In terms of instance size, Hibernate is not supported on bare metal servers. So if you have restored, let's say 500 GB of hard drive for a server, it won't work, it's not allowed. Supported AMIs are Linux AMIs, Ubuntu, some others. The root volume must be an AWS, it must be encrypted, cannot be an instance shop, and must be large enough to accommodate the memory dump file. Hibernate is only available for on-demand or reserved instances. Hibernation will not be possible due to the ephemeral nature of these instances. Finally, an instance cannot be hibernated for more than 60 days. That's it for the Hibernate mode. Now let's see how the Hibernate mode works. To do this, we'll launch an instance. All the images compatible with this functionality will appear. As we saw earlier, the hibernation mode is not available for all instances. So we have to get an instance that is eligible for Hibernate mode. Here we'll take the M5 lot. We get warned that this service is not free. We still have the same options when creating. Enable sleep behavior, enable hibernation as additional shutdown behavior. So we can see here that for this mode to work, there must be enough memory in the system. In order to store RAM, the volume must be encrypted. We click on Next. We get a warning that we need our volume to be encrypted so that it can support Hibernate mode. Similarly, we need this space to store our RAM and data. Let's increase the size. We're going to do 24 gigs. Once done, click on next. Now let's configure the security group. So I'm already in select a security group. So I'll take this one for example. It is allowed to communicate on the port 22. I check and launch my machine with my key pair. The machine is starting up. Once it is launched, we will connect to it. I'm going to log on to my machine, connect, and I will use EC2 Instance Connect mode. Directly from my console, my port 22 is enabled. I arrive at my machine, so I'm going to do an uptime. That's it, the machine starts, so I run the command again and it says the machine has been booted for 1 minute. Now what I'm going to do is I'm going to quit my instance and I'm going to shut it down. In the actions, shut down and hibernate. I agree. Machine is shutting down. I will restart in a few moments. Now that my machine has stopped, I have waited a few minutes. I will restart it. Now that it is restarted, I'm going to log back on, connecting, still using EC2 Instance Connect. This time, if I do my uptime, we can see that the machine has been running for 4 minutes. This means that while I stopped my machine, the system continued to run thanks to the hibernate mode. Now that this is done, it has been shown to work correctly. I'll shut it down now. I'll terminate the instance because it's a page service. That's it for hibernate mode. Let's go back to this first section. In this section, we have seen that EC2 instances are charged per second and that the T2 microtype is eligible to the free offer. On Macs and Linux, the SSC is used to connect to EC2 instances. The SSH is done on port 22 and for security reasons only allow it from your IP address. In case of a timeout, we have seen that the problem comes from the security group, probably from the port 22 being not open. If access is denied, it means that the permission on the SSH key is not good. Remember the options to change the CH mode 400 mode. Security groups can reference other security groups instead of an IP address range. That's very important. You must know the difference between a private IP, a public IP, and an AWS Elastic IP address. You can customize an EC2 instance with user data scripts. We have also seen that we need to know the different types of launch. We have seen the on-demand instances that we pay per second. We have seen reserved instances, spot instances who are much cheaper, up to 90% cheaper than on-demand instances, and the other dedicated ones. It is also necessary to know different type of basic instances. We saw that R was for RAM, C for CTI, M for medium, I for AEO, G for GPU, and T2/T3 for processor expansion. We have seen what the burst is. We also know now that an AMI can be copied from one region to another and from one user point to another. An EC2 instance can be started in a placement group. We have seen several placement groups as well as the cluster mode, spread mode, and the partition mode. In this lesson, we'll discover what a load balancer is. So let's take a deeper look at load balancing. A load balancer is a server that redirects all external traffic from the internet to multiple EC2 instances downstream from our load balancer. This little diagram shows the process. I have one load balancer here and 3 EC2 instances behind it. On the outside, I have a user 1 that will send a request to the load balancer. The load balancer will redirect this request to an instance, and the instance will respond to our user. We have a second user who will also make a request. This request will be transmitted by the load balancer to another EC2 instance, which will respond to our user number 2. In the same way, a user number 3 will communicate with the third instance, and so our load balancer will balance the external traffic and will redispatch it to our 3 instances in a balanced way, and that's why it's called a load balancer. So why use a load balancer? The load balancer, as we've seen, allows load balancing to multiple downstream instances. It displays a single point of access DNS to your application, meaning that no one from the outside will see your instances. Only the DNS name of your load balancer will be accessible from the outside. It manages transparently the failures of the downstream instances. In other words, if there is an instance that does not work, the load balancer will not send it a request. It also regularly checks the health of our instances. It provides an SSL access point and therefore HTTPS for our websites. It reinforces the adherence with cookies, but we'll come back to that later. It is a notion that we will not see immediately. It ensures high availability between zones. It separates public and private traffic. So why use an EC2 load balancer? An ELB or EC2 load balancer or elastic load balancer is a scalable load balancer. AWS guarantees the correct functioning. AWS supports upgrades, maintenance, and high availability. It provides simplified configuration tools. You will have 2 or 3 buttons to check the status of your load balancer. It is cheaper to set up your load balancer on your own by placing a server and security groups, but it will make more effort to maintain it. So the load balancer seems to be the best solution, that is to say the ELB. Indeed, it is integrated into many AWS service offerings. How does the load balancer check the health of our instances? It does so by doing health checks. It checks the health of the resources, so this is really a very important function of the load balancer. It's able to check, thanks to the health checks, if the instances are working or not. The health checks will in fact launch a request to the machine, and if the answer is not 200, that is to say OK, it means that the instance is not in a functional state or that it does not answer the requests. Here is a little diagram to briefly show you how it works. So we have our load balancer sending a health checks request to port 4567, and if it gets to 200 responses, the result is good. If it gets another response, it means that the health checks are not good, and the send checks will need to be changed. The different types of EC2 load balancer. So the classic load balancer version 1, the old generation that was created in 2009 by AWS. It supports HTTP, HTTPS, and TCP. Application load balancer version 2, new generation was created in 2016 and supports HTTP, HTTPS, and WebSocket. Finally, the network load balancer version 2, new generation of 2017, it supports TCP, TLS, which is in fact the secure TCP and UDP protocol. In general, it is recommended to use the latest version. The V2 generations offer more functionality. It is possible to set up another private internal load balancer that will allow your machines to communicate with each other to manage the traffic between them. It will not be accessible from the outside, or an external load balancer which is public, which can be used as an entry point for your external users, and which will also serve as an entry point for your machines. Load balancer security groups. Let's take an example. So we have a user, our load balancer, and the EC2 instance behind it. Our user will send an HTTP or HTTPS request from anywhere on our load balancer. And so to do this, our load balancer will have a security rules that allow requests on port 18 for HTTP and port 443 for HTTPS. And then the source 000/0, so from anywhere, and that's what we want. Then the load balancer will send the request from our user to our EC2 instance, and our EC2 instance will send the request back to the load balancer, which will forward it to the user. To do this, the application security group must allow traffic on port 18, but only from our load balancer. So we'll indicate in the security group to allow communication on port 18 only to the security group here. Which corresponds to the load balancer's security group. So we're going to do things differently. Our user has the right to connect to our load balancer on HTTP or HTTPS. Our load balancer is the only one that can connect to our EC2 instance, and our EC2 instance only allows the load balancer to connect to it on port 80. That's it for the load balancer security groups. Here are a few elements that are good to know about load balancers. You can resize a load balancer but not immediately. If you ever want the propagation to happen faster, you need to contact AWS. When troubleshooting a load balancer, there can be several types of errors. If there is a 400 error, it is an error induced by the client, that is to say from the outside. If we have a 500 errors, there are errors induced by the application. If you get a 403 error on the load balancer, it means that either the load balancer is overloaded or the target is not registered. If the load balancer fails to connect to your application, then you should check the security groups and see if the ports are open to your communications. For monitoring purposes, the ALB access log tracks all requests and can therefore debug on a per request basis. And that's it for load balancer. We will now look at our last type of load balancer, the network load balancer or NLB. The NLB is on layer 4 only. It allows to redirect all TCP or UDP traffic coming from outside and going to our instance. It handles millions of requests per second and has a very low latency of about 100 milliseconds, unlike the ELB, which has a latency of 400 milliseconds. The difference between the NLB and the CLB and ELB is that the NLB has a static IP address per AZ exposed to the outside world, which can be interesting if you want to whitelist IP addresses. In addition, unlike the other two types of load balancer, it supports elastic IP address allocation, which can allow us to have true entry points for our instances from our load balancer and our NLB. NLBs are used for very high performance in GCP or UDP. You have to be very careful because this is an option that is not part of the free offer. Let's see the diagram. We have our network load balancer as an entry point. We still have our application with our two instances communicating with the outside. Except that this time our application will see TCP traffic coming directly from the outside in both cases. We'll see how this plays out on the console directly. So we're going to create our network load balancer, which communicates over TCP, TLS, which is secure TCP in UDP. So we click on create. Here I'll call it my NLB. It will communicate through TCP on the port 80. We'll do it through several ability zones. We'll configure the routing. Here we'll call our target group my NLB group. The target type will be an instance, the TCP protocol on port 80, and the health checks level will be on TCP, the traffic port. Regarding the health check threshold, things seem to be set properly. We're just going to put it in 10 seconds to make it faster. That's it. So we are going to add our instance to our target group. We click on next and let's make a last check. Then we create our load balancer. We are going to be able to test our NLB. As you can see, it doesn't work, but that's normal because in fact, if we go back to the load balancers, you can see that there is a difference between my ALB and my NLB that we just created. When my LLB was created, there was a notion of an associated security group, whereas when we created my NLB, there was no such notion of a security group. To solve our problem, we go to the target group. And in our target group, we're going to select one of our machines and we're going to go and modify a security group properties. To do this, we'll add a rule, a custom TCP rule on port 80. set as from anywhere, and we'll say it's for the NLB. We save the changes we have made, and now you're aware of how a network load balancer works. Now let's talk about load balancer adherence. It is possible to implement load balancer adherence so that the client is always redirected to the same instance behind the load balancer. This works for LAB and CLB. The cookie used for adherence as an expiration time that can be controlled. The most common use cases are to ensure that the user does not lose their session between two requests or queries. The problem with this method is that it can unbalance the load on the downstream instance of the load balancer because it is no longer balanced, it is fixed on a single machine. So it can overload our backend procedure. To make a small diagram, we have our load balancer here with two instances behind it. We have a client 1, here we'll make a first request, which will go to the other instance. When using adherence and making a second request, if cookies are still valid, the user falls back on the same instance. In the same way with client 2, the load balancer will redirect the user to an instance, and if he ever reconnects in the same way as client 1, as long as the tool is valid, we want him to fall back on instance number 2, and the same way for client 3. Let's see how this manifests itself in the console. Back in the console, so we are on our load balancer. In terms of adherence, it's not at the load balancer level that is going to happen, but it's going to be at the target group level. We are already going to see what the current behavior is by going to load. We refresh the page, we are redirected to different instances. So now we are going to set up the adherence at the target group level. Here, modify the attributes we activate. We'll set the duration of the permanence at 2 minutes per membership. Now if we go back to our page and refresh, the time it takes for the option to be activated is now set at 2 minutes and we will be redirected to the same instance. So this is how the adherence works at the level of the balancer. It is managed at the level of the site. In this lesson, we'll see how to manage SSL certificates in AWS. We will review the basics of SSL. So we have already seen this diagram. We have our user who is going to connect to our load balancer in HTTPS, this time with an encrypted connection from the internet. What will happen with the load balancer? Well, we'll have a connection termination and then the traffic will be forwarded to our instance in HTTP on the private network. The load balancer uses an X509 SSL TLS certificate, which are server certificates. These certificates can be managed with AWS Certificate Manager. You can create your own certificate and upload it to AWS. At the HTTPS listener level, a default certificate must be specified. A list of certificates can be added here to support multiple domain names for multiple websites. A client machine uses the server name indication service to identify the server they are trying to reach. Policies to support older version of SSL/TLS on legacy clients with legacy security policies are also possible. When it comes to NIS addresses, there is a problem regarding the loading of multiple certificates on a single server for multiple websites. This is a new protocol that requires the client to specify the name of the target server during the first SSL negotiation. The server will then find the corresponding certificate or provide a default certificate if available. Note that this only works with ELB and NLB next generation load balancer or CloudFront, but does not work with the classic load balancer. Let's take an example. We have our LIB and therefore our load balancer for our applications. We have two linked websites, www.ut.com and www.munok.com, which will correspond to two target groups. And for these two target groups, we'll have two certificates corresponding to the websites of the target. Our client will ask our load balancer, I want to connect to www.ut.com. At this point, our load balancer will search its certificates for the corresponding certificate, and then redirect us to the right target group. If we're not given any particular indication, or if you want to go to the default site, the default behavior of our load balancer will be to provide us with the certificate that it has by default, and that will take us to munok.com. Now about Elastic Load Balancer and SSL. Here we're going to talk about all our load balancers. So we have the CLB, which is in version 1. It only supports one SSL certificate, and if you want to publish several websites, we'll need several load balancer, several CLBs with several certificates for each website. In the case of the application load balancer, so ALB, which is in version 2, new generation, it supports multiple SSL certificates. It uses server name indication to operate. And similarly, our network load balancer, NLB, in the next generation also supports multiple SSL certificates and will also need SNI to work. Now let's see in our console how this will manifest itself. We'll click on our CLB, and in the listeners, we'll modify the listener here by adding the secure HTTPS protocol port 443. And here we can choose the encryption method. Here we have the choice between several protocols and several options. We save once we have made our choice. And there we can indicate a certificate we want to select. We can load a certificate into IAM. We don't have one at the moment. We can select an existing certificate, but we haven't loaded one yet, so for the moment we'll just view it. We can also choose a certificate that is stored in ACM, which is the method recommended by AWS. Once this is done, we can connect in HTTPS with an authenticated certificate through our CLB. Now let's look at our ALB. Here we can add a listener in the same way. This will be an HTTPS listener. The default action, let's say, forward to my target group. Here you can define the security strategy. We can also choose a certificate either from ACM or from IAM or from import. We are not going to do that here, so they allow us to add different rules here and redirect them to different target groups and add multiple certificates. So I'm out. Now we're going to look at our network load balancer. We're going to look at the listeners, and in the same way I'm going to be able to add a listener. This time it will be a TLS listener. So in the same way, we'll be able to choose a certificate either from ACM or from IAM or from importing. That's it for SNI and load balancer. In this lesson, we'll see how to manage SSL certificates in AWS. We will review the basics of SSL. So we have already seen this diagram. We have our user who is going to connect to our load balancer in HTTPS, this time with an encrypted connection from the internet. What will happen with the load balancer? Well, we'll have a connection termination, and then the traffic will be forwarded to our instance in HTTP on the private network. The load balancer uses an X509 SSL TLS certificate, which are server certificates. These certificates can be managed with AWS Certificate Manager. You can create your own certificate and upload it to AWS. At the HTTPS listener level, a default certificate must be specified. A list of certificates can be added here to support multiple domain names for multiple websites. A client machine uses the server name indication service to identify the server they are trying to reach. Policies to support older version of SSL/TLS on legacy clients with legacy security policies are also possible. When it comes to NIS addresses, there is a problem regarding the loading of multiple certificates on a single server for multiple websites. This is a new protocol that requires the client to specify the name of the target server during the first SSL negotiation. The server will then find the corresponding certificate or provide a default certificate if available. Note that this only works with ELB and NLB next generation load balancer or CloudFront, but does not work with the classic load balancer. Let's take an example. We have our LIB and therefore our load balancer for our applications. We have two linked websites, www.ut.com and www.munok.com, which will correspond to two target groups. And for these two target groups, we'll have two certificates corresponding to the websites of the target. Our client will ask our load balancer, I want to connect to www.ut.com. At this point, our load balancer will search its certificates for the corresponding certificate, and then redirect us to the right target group. If we're not given any particular indication, or if you want to go to the default site, the default behavior of our load balancer will be to provide us with the certificate that it has by default, and that will take us to munok.com. Now about Elastic Load Balancer and SSL. Here we're going to talk about all our load balancers. So we have the CLB, which is in version 1. It only supports one SSL certificate, and if you want to publish several websites, we'll need several load balancers, several CLBs with several certificates for each website. In the case of the application load balancer, so ALB, which is in version 2, new generation, it supports multiple SSL certificates. It uses server name indication to operate. And similarly, our network load balancer, NLB, in the next generation also supports multiple SSL certificates and will also need SNI to work. Now let's see in our console how this will manifest itself. We'll click on our CLB, and in the listeners, we'll modify the listener here by adding the secure HTTPS protocol port 443. and here we can choose the encryption method. Here we have the choice between several protocols and several options. We save once we have made our choice, and there we can indicate a certificate we want to select. We can load a certificate into IAM. We don't have one at the moment. We can select an existing certificate, but we haven't loaded one yet, so for the moment we'll just view it. We can also choose a certificate that is stored in ACM, which is the method recommended by AWS. Once this is done, we can connect in HTTPS with an authenticated certificate through our CLB. Now let's look at our ALB. Here we can add a listener in the same way. This will be an HTTPS listener. The default action, let's say, forward to my target group. Here you can define the security strategy. We can also choose a certificate either from ACM or from IAM or from import. We are not going to do that here, so allow us to add different rules here and redirect them to different target groups and add multiple certificates. So I'm out. Now we're going to look at our network load balancer. We're going to look at the listeners, and in the same way I'm going to be able to add a listener. This time it will be a TLS listener. So in the same way we'll be able to choose a certificate either from ACM or from IAM or from importing. That's it for SNI and load balancers. We will now create our first scaling group, or ASG. For this we need a load balancer. We don't have any running instances, so we'll create our auto scaling group. We're going to be on the old AWS interface, which ends on August 31st, so we'll switch to the new version. On the home page of our auto scaling, we'll create an auto scaling group that we will call My First ASG. As a launch model, we have none. So what we're going to do is we're going to create a launch model. My first ASG model. I'll also use this as a description. We turn off the advices regarding auto scaling. Model targets are not needed at the moment. We'll choose the type of AMI. We'll choose an Amazon Linux 2. And the instance model will take a T3. More precisely, T3 micro. We'll check our key pair, my first instance. We'll use a VPC. We'll use the same security group as before, that is to say my first instance group, which will authorize on port 22 and 80. We have an ABS storage volume. Tags can be used, but I'm not going to use any at the moment. We've made good progress here. Network interface will use the primary interface. What's interesting is details in which we can put the user data. We'll get the script. We insert the user data, and remember that this script allows us to install apache and display a message on the home page. We confirm our selection and then create. I'll now display my instant template. It is well created. Now I can go back to my ASG page, and so I refresh. And here I can choose my first EAG template. So it has all the information that we put in it, the launch template, the security group, and the information that is active in our launch template. I do the following. We have two solutions here, combined spot instances and on-demand instances, or use on-demand instances only. We'll use on-demand instances. We are going to restore our machine on the default VPC and the 3 availability zones. We do the following. Regarding the load balancing, we're going to activate the load balancing, so we're going to be on an ELB, so an application load balancer, and we're going to select here. We select the target group in which our machine will be located. When it comes to health check, the EC2 health check is activated by default, and we can also turn on the load balancer health check. We don't need to activate monitoring for the moment. We'll come back to it when we study CloudWatch. Here we have the possibility to configure the scale of our group. The desired and minimum size is 1 and the maximum size is 3. We confirm our choice. Concerning the scaling strategies, we don't care about it for the moment. Same for the instant protection against scaling. Regarding notification, we can send notification through the AWS service. In our example, this is not necessary. We can also add tags, but again, this is not necessary. We can then create our auto scaling group. We arrive on the page of our auto scaling group, click on it. We'll see that at the level of the capacity, we have the desired one, the minimal one, and lastly the maximum one. If we go back to the previous page, we can also see that our group has just launched an instance in this ability zone. We can have the information related to the activity of our auto scaling group. We can see that a machine has been launched following the group's request. The capacity has changed from 0 to 1, which corresponds to the desired capacity. We can now check in the target group of our load balancer if the auto scaling group has added the target, that is to say our machine. We can go back to the load balancer in order to connect to the web page and check that it is working properly, in particular to see if a desired message is displayed. I copy the address and wait a few seconds. The desired message appears. We'll be able to modify the strategy of our auto scaling group. In order to modify the minimum expected number, we return to the page of our auto scaling group. We click on the desired group and we can now edit the capacity. The desired capacity is changed to 2. The other parameters are not changed. We will now look in the Activity tab if the data has been updated. After refreshing the page, we see that our group has decided to launch a new EC2 instance to respond to the author's count request. That is to say, our new request for the desired capacity. We refresh again, the second instance has been launched successfully. We go to our target group and see that the second instance has been added. Both are healthy. We go back to our load balancer and we refresh the page. We'll see our two instances responding to the browser request. Thanks to the auto-scaling group, we can feed our load balancer according to the policy we have undertaken. That's it for our auto-scaling group. We'll study the different scaling strategies. We have target tracking, which is the simplest and easiest method to use. We will define a target to reach and a behavior to adapt according to this one. For example, we want the average CPU of my SCAG to be 40%. If the 40% is exceeded, then we'll auto-scale by either reducing or adding a certain number of machines. There is another strategy that is just as simple, but this time it is step-by-step. We'll define a CloudWatch alert, for example, CPU over 70%. In this case, we'll have a trigger that will add instances. In the same way, we'll have an alert that will tell us when the CPU is below 30%. In this case, we'll have a trigger that will remove instances. We can also have a planned strategy, for example, that will foresee a load increase at the end of the week to cope with the increased demand on weekends. For example, we'll decide to add instances on Friday afternoons between 5 p.m. and 8 p.m. There is also what is called scaling cooldown. This prevents the ASG from launching or terminating additional instances before the effects of the previous scaling are visible. During new scalings, there is a 300-second period during which our ASG will let the machine start, and only at the end of this countdown will it consider a new request. We can create personalized progressive stabilization strategies in order to reduce the default time to something shorter. The created strategies have more importance than the default ones. If a 300-second period is too long, a 180-second period can be applied. If your application frequently reduces which increases its number of instances in a given period. Change the stabilization time in the CloudWatch alerts that trigger scaling. If we wait 10 minutes, we have a load increase, which implies the creation of a new machine. If we have to wait 300 seconds, we risk losing quality. This diagram, taken from the AWS website, shows the following. There are several possible actions. We have a scaling that is taking place. We are going to ask the question, is the coolant period still in progress? If so, we ignore the new scaling. If the answer is no, we reduce the number of machines or increase it. Let's see how it looks in the console. Now back to our ASG, we have the details of our group, the desired capacity, the minimum capacity, and the maximum capacity. We can see that we have our two instances. The desired capacity corresponds to the number of activated machines. We'll add a scaling strategy. We have to choose between target tracking, step scaling, or simple scaling. The last two are very similar. We'll opt for a scaling with target tracking, which we'll call target tracking policy. We are going to look at our average CPU usage. We'll choose other factors, the average number of incoming and outgoing visits. Let's stay with the CPU and say that our target value is 30%. For stability, we'll overload the value of 300 seconds. We'll put 10 seconds for a faster startup. We'll create our scaling strategy. This is our scaling strategy with target tracking. The queries we filled in earlier are present. We now look at our activity. We can now see that our auto scaling group has defined that our capacity is far too high in relation to the indicated target. We are going to get rid of a machine. As you can see, we have an alarm here, triggered by the security policy, which makes us go from 2 to 1 capacity to meet our requirements. We can see that one of our instances is shutting down. In the instance management, we can see that one is being terminated. Looking at the ASG details, our desired capacity has been reduced to 1 machine instead of 2. Here is a first example of automatic scaling by target. We will delete this one for now. We'll be able to create a planned version. We'll call this one the Friday update. The minimum capacity will be 10 machines. The recurrence will be once a week. We will define the date. We'll say Friday at midnight. It is preferable to choose a date that is not earlier than today. We confirm and create. As you can see, the desired program has been created. It will start on Friday and will set up 10 machines. You still have to be careful with the other scaling group. You can accidentally delete an instance, but the scaling groups will recreate them. That's it for the scaling groups.
In this lesson, we will see what an EBS or Elastic Block Storage Volume is. We have seen that when we use an instance and we turn it off or terminate it manually, we lose our storage space or hard disk. Accidental terminations may also occur from time to time. At that time, you will receive an email alert from AWS. We can also need to store data related to our instances in a punctual way and thus have a storage medium independent from our instances. An EBS or Elastic Block Store Volume is a network volume that we can attach to our instances on the fly. You have to imagine it as a USB key on the network. This allows instances to have persistent data. The EBS volume itself is a network resource. It's not a physical hard disk attached to your instance. It uses the network to communicate with the instances, which means there may be some latency when using an EBS volume. It can be detached or attached to another instance very quickly. EBS volumes are bound to an availability zone, which means that the same EBS volume cannot be used on two availability zones at the same time. You can't retouch, so there you go. Let's take the example of a EU West 1A zone. We will not be able to attach any volume from this zone to the other zone, EU West 1B. In order to move a volume, it's necessary to take a snapshot of it upstream, and then restore it in another availability zone. We can increase the capacity in terms of disk space in giga or tera, but also increase the number of input and output operations per second. We have to be very careful because we are built according to the capacities supplied. If I supply 30 gigas and only consume 1 giga out of the 30, I will pay for the 30 gigas. The size of the volume can be increased over time as well as the input and output operations. The idea is that for EBS volumes, it's to start small and grow as storage needs increase over time. An example of the use of our EBS volumes between several zones. So here we have a zone with our 3 EC2 instances. So the first one is attached. It has an EBS volume of 10 gigas attached. Our second instance has two attached volumes, one of 100 gigas and one of 50 gigas. And our third instance has no EBS volume attached. In our second zone, we will have two instances. One will have a volume of 50 gigas attached and the other will have nothing. What we have to understand here is that our three volumes here can be exchanged and reassigned to the different instances of the same zone, but that cannot be used by the instances of another availability zone. We'll see later on how to move a volume to another availability zone. There are different types of EBS volumes. There are four types of EBS volumes. The GP2, which is dedicated to general purpose use with a good balance between punch and performance and is suitable for a wide variety of workloads. The IOI1 is a very high performance SSD, ideal for critical tasks requiring very low latency or very high throughput in terms of disk writing. The STI is a low-cost hard disk ideal for tasks requiring frequent accesses with a high throughput like big data and with a high demand in terms of writing. An SCI, which is the cheapest disk, the cheapest volume type, is also ideal for big data tasks with less frequent disk access. Volumes can be characterized by their size, flow rate, input and output operations per second. If you are in doubt, I invite you to consult the AWS documentation, which is very complete on the subject to know if you choose the right type of volume for your instances. And finally, you should know that only SSDs, GP2 and ION1 can be used as boot drives. You can only install a bootable operating system on these two types of EBS volume. Now let's get down to practice and create our first EBS volumes. To do this, we will go to our EC2 console and we will launch an instance. We will, as usual, take our Amazon Linux 2 in T2 Micro because it is eligible for the free offer. As for the instance details settings, I'm going to leave everything as default since we are dealing with storage here. So we arrive here on Add Storage. So we have our word volume on which our operating system will be installed, which has 8 GB. This is a GP2 disk. One could choose IOPS or standard DHDD low-cost magnetic disk. We will see later on the notion of IOPS, which means input and output per second. Here it's possible to choose the behavior at standstill. You can delete the termination or not. You can encrypt our disk or not. We won't encrypt it here because this is not what this module needs. Let's have some fun. We will add an EBS volume that we will mount on dev SDB. The snapshot is not needed for the moment. We will see later when we have created it how to restore our volume from the snapshot. We will set the size to 2 GB. We will stay on GP2. The default options, here the character delete on termination. Since the data persists on this disk, we will keep it, which means we will not delete it when our instance is terminated. In the same way, we will not put a figure on it. Here we can see that customers eligible for the free offer can get up to 30 GB of general purpose EBS, SSD or magnetic storage. I will therefore be able to accumulate up to 30 GB of storage space for one instance. We will add a tag in order to identify our EBS storage spaces. We'll put a tag name. And we will say it's going to be EBS demo. At the security group level, we will select an existing security group, the one of my first instance, which guarantees us access to port 22, at least for SSH. I check and I launch my instance. At the key pair level, I keep the use of my initial key pair from my first instance. My instance is being launched. Our instance is launched, so here we can find the information about our storage volumes. We have the root device on which is installed our boot tape, which is on our first disk of 8 GB/dev/xvda. This volume is also a volume in block mode, so it appears below with our /dev/sdb. We will click on our volumes. We see how it's organized in terms of our volumes in the AWS console. We can see here in the EBS demo that I have a volume here that corresponds to our root volume of 8 GB and here our additional volume, an EBS of 2 GB that has been added. Now that we have our two volumes running, we can connect to our instance to see how it looks inside the system. To do this, we will connect to our machine. Here we are connected to our instance, and so to check the state of the hard disk, we will launch a basic Linux command. To list our hard drives and for editing. We can see here that we have our XVA disk with a XVVA1 partition whose mount point is / thus the root of our system. We have our second volume XVDB, which is not yet mounted in our system. So that we are going to do is we are going to edit our volume in our system. So for that, we will refer to AWS documentation. Here we are on the AWS documentation and we can make an Amazon EBS volume available for use on a Linux system. Just follow the documentation. The first command we executed is the svlk command, which allows us to see what volumes exist on our system as well as the mount points associated with these volumes. We carried out our order and we saw that we had two partitions, one of 2 GB and one of 8 GB with a point of mounting / for the first and no point of mounting for the second. In the documentation, it's explained to us that to know the type of file system that is installed on our volume, we must execute the command file -s with the name of our volume as argument. So we will execute this command. So sudo file -s from /dev/xvdb This returns data to me, that is, there is no file system mounted as explained here. If we have this, it doesn't work. If we have a file system installed on our volume, we will have more information like this. We will continue reading the documentation and we will create a file system on our volume. For this, we have the command mkfs-t xfs, which will be the type of file system. We will use ext4, which is the standard on Linux servers. We will execute the command mkfs-t. In ext4 from /dev xvdb. We have some information that has come in, so our formatting has been done well. I clean my screen. If there is an error like mkfs.xfs cannot be found, you can always solve this problem by installing xfs procs, which is a distribution kit. We didn't have that problem, so we will move on to the next step. What we will be able to do is to create the folder in which our volume will be mounted. mkdir/data. Then what we are going to do is we are going to mount our volume on this file. We will execute the command sudo mount. /dev xvdb. in/data. There is no mistake. We will redo the lsblk command to see if we have something mounted. Here we can see that we have xvva, our 8 GB root disk that is always mounted on the root /, and now our xvdb, which is mounted on /data. We will have the possibility to move in /data to create a file. hello.txt. We need to correct rights, sudo, sudo touch hello.txt, and we will be able to go into this file and write a message. Hello to all. We save, and we find ourselves in our newly mounted volume with a hello text file including a hello to all message. We continue to read the documentation. Now that this is done, we have the possibility of making this mount point persistent after the reboot, because this is a one-time operation, so each time we reboot our machine, we will have to remount our hard disk. To do this, we will modify a configuration file called /etc fstab. We will save this file before modifying it. So sudo cp/etc fstab in /etc fstab.origin. Now we can modify our file sudo nano /etc fstab. Here we already have a volume that is mounted. What we are going to say is that we are going to mount our volume, which is at /dev/xvdb. Then we will indicate the folder in which we want to mount our volume, so in /data. We will also indicate the type of file system, so ext4, and then we have default values, so here are defaults, no fail, 0 and 2. We will save our file. We restart our machine, so we did a reboot. If we run our lsblk command again, following the modification of the fstab file, we find ourselves at reboot with our second partition, our second EBS volume mounted in /data in our instance. Let's now take a look at the different use cases for EBS volumes. As we have seen, we have several types of EBS volumes. We will start with GP2, which is recommended for any type of workload. It can be used as a boot disk for MBR installation or a boot tape. It can be used in an office environment to make virtual desktops. It can also be used for interactive applications that require low latency, such as web applications with user interaction. It can also be useful in test and development environments because there are many possibilities with this type of hard disk. The size of these hard drives can vary from 1 GB to 16 TB. GP2 volumes support burst mode and can extend their input and output IOPS capabilities to 3000 operations per second. The maximum volume of IOPS is 16,000 operations per second. This means that if we have 3 input and output operations granted per gigabyte of our volume, we reach the maximum number of input and output per second when our volume has a size of 5,334 gigabytes. Let's see how to create an EBS volume in GP2 in the console. For this, I go back to my EC2. I will go into the volumes and I will arbitrarily create a new volume. Here I can define the type of volume. We want a GP2 in SSD. We will be able to define the size in gigas of our volume with a minimum size of 1 giga and a maximum size of 16,384 gigas. Here we see that for 100 gigas we have 300 input and output operations per second out of the 3000 that we can have at most. What is interesting to see here is that if we change the size of our hard disk, we put for example 1500 gigas, we will have 4500 input and output operations per second. There is therefore an interaction between the size of our hard disk and the number of operations that we can benefit from in relation to the size of the same hard disk, knowing that if we go below 1 giga we will have 100 input and output operations per second, and if we exceed 5344 gigas, as we saw in the previous reading, we will be at 16,000 input and output operations per second. Here we have the availability zone, so we can see that we are well fixed to our given availability zone. The flow rate does not apply to the GP2 disk. We can eventually choose a snapshot to create our volume from an already existing image. We can also quantify our volume at this level. Let's move on to the next type of volume. We will switch to the IO1 volume type, which is recommended for commercial applications requiring very sustained input and output performance that exceeds the GP2 disk limit of 16,000 inputs and outputs per second per volume. When the limits of GP2 are exceeded, it's necessary to switch to IO1. Supports large database workloads such as MongoDB, Cassandra, Microsoft SQL, MySQL, PostgreSQL, or even Oracle. The size of these volumes can vary from 4 GB to 16 TB. And we can supply inputs and outputs independently of the size of the hard disk, so we can have a variable size hard disk with variable IOPS. For IOPS, we are at a minimum of 100 for a maximum of 64,000 inputs and outputs per second for Nitro type instances, but they are not part of this training. Generally, we will have machines that can run at 32,000 operations per second, but we will first see how this is set in the console for an IO1 disk. Back in the console, we can choose an IOPS disk provisioned on SSD. We will be able to define the size of our hard disk. Let's say, for example, 1000 GB of hard disk for the minimum IOPS. What will be interesting to note here is that if we change the size of our hard disk, automatically our input and output volume is modified accordingly. There are some limitations. We are still at a 50:1 ratio, so for a giga you have 50 operations per second, and so that was what was interesting to see with this type of volume, while knowing that the rest of the options remain the same. Let's now look at our third type of EBS volume, which corresponds to an HDD type hard drive, so it's not SSD but rather recommended for streaming applications requiring a fast and constant throughput for a rather low price. It's ideal for big data warehouses and log analysis such as Apache Kafka, or applications that use a lot such as Elasticsearch or these kinds of things. It cannot be used as a boot disk. It ranges in size from 500 GB to 16 TB with input and output operations scalable to the maximum of 500 operations per second. These hard disks have a reading and writing speed of 500 MB per second, which can be extended with the burst principle that we have already seen in the different modules we have studied. Let's now see the SC1 model. Corresponds to a cold installed hard disk. It is therefore necessary to stop the machine to reattach the EBS volume. What will be interesting is that compared to the size of our hard disk, if we are at 1000 GB for example, we see that here our throughput, our number of megabytes per second in terms of writing and reading, is 12 out of 79. The more we increase the size of our hard disk, if we go for example to 16 tera, here we see that we will increase. The most important thing to remember about the STI instance is that the larger the hard disk, the more reading and writing capacity you will have. So we are going to put the maximum to make it more meaningful, so 16,384. 192. It's funny, we don't reach the limit, but it's a type of volume that also has extension capacities, the burst as we have seen, and it's therefore completely modifiable and evolutive. Now let's look at our last type of EBS volume, the SC1, recommended for applications requiring good throughput on large volumes of data but with little file access, so it's a service account that will access all the files and not a very large traffic. This may be important in projects where the cost of storage should be the lowest. Indeed, like the other type of HDD disk, the ST1, this disk cannot be used as a boot disk. Size can vary from 500 GB to 16 tera. Its volume on input and output operations per second is capped at 250. It can be extended with the concept of burst, thus extended the capabilities for our instance. You can see in the console how it works. In the same way, ST1 will be selected here. As you can see, with a minimum size of 16,384, I reach the maximum in terms of throughput. If I scale down here, I can see that I'm down to 40 megabytes per second with an expression capacity of up to 245. It can be fun to play with, but for the moment it's not very interesting. We'll do a quick summary of everything we have seen in this section. The important thing to remember about our EBS volume is that we have GP2 volumes which are for general use and are very low cost. There is a ratio for 3 input and output operations per second per gigabyte with a minimum of 100 input and output operations per second. This can be extended to 3000 operations per second with a minimum of 16,000 in extended capacities. The size of this type of disk can vary from 1 GB to 16 TB, and for each terabyte added, there can be 3000 input and output operations per second. Then we have the IO1 disk type with an IOPS supply independent of the disk size. This is more expensive, but you can define the number of inputs and outputs you need independently of the disk size. With a maximum of 64,000 IOPS for the Nitro type instances that we will not see in this training, or 32,000 for all other instances including Linux AMI or T3 micro or T2 micro that we have been using since the beginning of this training. The size of this disk can vary from 4 GB to 16 tera, and the size of the volume, as I explained to you, is independent of the number of IOPS. We have also seen ST1 type disk, which are hard disk optimized for throughput per second. So this disk can range in size from 500 GB to 16 teras and offer a read speed of 500 MB per second. SC1 hard disks are similar in nature to ST1 disks, except that these disks will have less solicitation from users and are therefore useful for applications such as big data, data analysis, and so on. With a single service account, for example, we will be able to support everything with a throughput of 250 megabytes per second and with disk of 250 gigabytes at 16 terabytes. So much for our little summary of EBS volumes. In this lesson, we will discover that our EBS instances can be saved as a snapshot like in a classic hypervisor like VMware or VirtualBox. The backups or snapshots of our EBS volumes are incremental. Only the modified data, only the modified blocks are saved. Backing up a volume uses the input and output of your disk, so it's recommended not to back up during traffic peaks, especially in moments of dead calm. These snapshots are saved on S3 but will not be visible directly in S3. You have to be very careful because all storage in S3 is paid for, so if you have snapshots, know that you are paying to store them. It's not necessary to detach a volume before making a snapshot, but it's recommended in the AWS documentation. Up to 100,000 snapshots can be taken for AWS accounts, thus for the root account for an entire organization. This leaves room for improvement, but the cost is still quite high compared to S3. I remind you that it's paid for and it's stored on there. A snapshot can be copied from one region to another and from one availability zone to another. This is done by creating an Amazon image from a snapshot. Since our volumes are locked to availability zones, in order to move them from one zone to another, we will have to make a snapshot, copy it to another zone and restore it in this other zone in order to have the contents of our image. EBS volumes restored from snapshot need to be initialized using dd and fio commands to read the entire volume, lsblk to get the information, and mount mkfs for all the commands we saw earlier to mount our volume. Snapshot generation can be automated using the Amazon KMS Data Lifecycle Manager. We will come back to this tool later in this training. Let's take a look at the console to see how this is demonstrated. Now let's imagine that I want to create a snapshot of the volume on which I created my hello.txt file with a hello everyone message. I will have several options: modify the volume, create a snapshot, force the detachment of the volumes, and so on. Here, what will interest us is to create a snapshot. I will call it my snapshot. It can be encrypted. We can add a tag, but we won't for the moment. In any case, we will not create volume. We have the volume ID, the description that is not encrypted. Create snapshot, creating snapshot fail, hide details, API error message, value mass snapshot invalid, character sets beyond ASCII are not supported. You should not use capital letters. I guess that must be the mistake. We create our snapshot, there it is settled. We close. We will be able to check if we have a snapshot, and indeed we have one. Maybe we should have put a tag on it. We click on it, we have information related to our snapshot. What will be interesting is that we will be able to have several actions on our snapshot. We will be able to delete it, create a volume from our snapshot, so there will be the message "Hi everyone" in the /data. We will be able to manage a fast snapshot, thus restoring the image quickly in the event of a failure that is detrimental to the business. Create an image from this snapshot, copy it, and we will see it a little later in the volume copy to other availability zones or other regions. Change permissions, add or modify tags. What can be interesting to do with snapshots eventually is to take a look at the lifecycle manager. We can therefore define a strategy for the lifecycle of our snapshots. We will say that, for example, it will be instant 1. Select the type of resources to backup, so it will be a volume. We will target the following tags. All volumes whose name correspond to EBS demo, so the name of our additional volume. We will be able to define a behavior with respect to each of the instances that will come from the EBS demo. How will it work? We will be able to define a plan. We will keep the default name with a frequency that can be daily, weekly, monthly, or annually. We will say, for example, weekly, this Sunday. At a time when we don't have much activity, Sundays are usually good. We will be able to define the type of conservation either in number or in age, at the level of the year or at the level of the number of days. For example, if I put 7, I will have the guarantee that I will have a snapshot taken every week, every Sunday at 9 o'clock in the morning, and I will have a conservation of 7 images, meaning 7 snapshots which correspond to 7 backups on 7 days of my volume. We can use S3 for backup, but managing the lifecycle of our snapshot can effectively offset the overhead of using S3. We're already using S3 to store our instances. This is just a personal point of view, so we can also define an IAM role or a group. For the moment I don't have much because I'm at the beginning of the training, but I will certainly have more later. But clearly it can be a very good way to manage the backup and permanence of our information in Amazon Web Services. I think that's all for this module. Let's take a look at the migration of EBS volumes. EBS volumes are, as we have seen, linked to one availability zone and only one. To migrate a volume to another availability zone or even to another region, you must create a snapshot of that volume. Copy this volume to another region or availability zone. Create a volume from the copied snapshot in the destination area, so that you can recreate a volume from this snapshot. Let's see how this is demonstrated in the console. Back in the console, we will go back to EC2. Then we will go and look in our snapshots. We will have several options on our snapshot, which is here. We can create a volume from our snapshot. We will keep the initial options, so a GP2 at 2 GB. Still with the same IOPS options. Now what we can do is, from our snapshot, move our volume to another availability zone. We will say 3C, for example. Of course, we can have the default options, encryption, sizes, and so on. We will create our volume. If we go back to our volumes here, we can see that our volume is being created. It's available. It's based on a snapshot. Corresponding to one of our previously created volumes. It's a very short, very simple module, so you can migrate volumes from one area to another or from one region to another quite easily. In this part, we will discover the encryption of EBS volumes. When encrypting an EBS volume, it has the following effects. The static data on the volume is encrypted. All data exchanged between the instance and the volume is encrypted on the fly. The snapshots we can take of our volumes will also be encrypted. All volumes created from the encrypted snapshot will be encrypted as well. Encryption or decryption is handled automatically and transparently. So there is nothing to do in the console since everything is done automatically with the AWS KMS. Encryption has a low impact on latency, so it doesn't hurt to enable it for your volumes. It has a very low impact on performance. The encryption level of the keys managed by the AWS KMS, it has the AES 256 level. This is quite common and secure. Copying an encrypted snapshot enables encryption on the final volume. Snapshots that I have become encrypted are also encrypted. To create a snapshot of a volume, the method is as follows. We can encrypt the snapshot using the copy. You can create a new volume from the encrypted snapshot, at which point the resulting volume will also be encrypted. It's then possible to attach the new encrypted volumes to the original instance. We will see how it goes in the console. Back in the console, we will go and look at our volumes. We have the two volumes that we created with our instance. And here we have the volumes that we copied from it, which is not encrypted but is available. We can also see here that its encryption status is not encrypted, so to be able to have this disk encrypted, we will go and check the status of our snapshot. Here we see that our snapshot is not encrypted, so we will make a copy of our snapshot. We will stay in the same area, copy from my snapshot. And we will encrypt this snapshot with the default AWS key. We validate, we close. Now I have my encrypted snapshot that is being created. Our snapshot is now created. We can see here that the snapshot is encrypted with a KMS key allocated by AWS EBS. Now we can go back to our volumes and we will be able to create a volume. We will stay on GP2. We can redefine the size to 2 GB. We will stay on the same availability zone, EU West 3A. For the snapshot ID, we will choose our encrypted copy. I think it's this one. Here we can encrypt the volume from the snapshot. We will create our volume. For the main key, we put the default one. We can create our volume and close. Then we can attach our volume to our instance, provided of course that our instance is in the same availability zone as our volume. Here it won't work because I have my volume in the EU West 3A zone while my instance in the EU West 3B zone. But we understand the concept, so we create our volume from a snapshot and we will be able to redefine the zone of availability. That is to say, to move my other volume from a zone or a region to another. And we will be able to attach to our machines as long as we are on the same availability zone. So much for the encryption and decryption of EBS volumes. We will now see the differences between an EBS volume and an instance store. Some instances do not come with an EBS volume as root volume. Instead, they come with an instance store that corresponds to ephemeral storage. The instance store is physically attached to the instance, so think of it as a physical hard drive that is in the same computer rack as the server where your instance is located. While the EBS volume is a network drive. Why use the instance store? It has better input and output performance since the link between the instance and its volume is a physical link. This is ideal for buffering, caching, working data, or temporary content. The data is kept when the instance is restarted, which can be interesting in an operating mode. The disadvantages: upon shutdown or termination, the instance store is lost along with any unsaved data from that volume. You cannot resize an instance store. Once you have provisioned, let's say 8 GB of instance store, you can't change that act anymore. It's therefore necessary to plan the use of our ephemeral storage of our instance stores. And indeed, if you want to make a backup of our volume or of the data it contains, we will be obliged to carry out a manual task inside the system, a kind of copy to another type of support that is not ephemeral. Otherwise, the backups are made manually and we could therefore lose our data if we don't make them. What is the benefit of using a local EC2 instance store? We have seen that it's a physical disk that is physically attached to the server where the instance is installed. It therefore guarantees very good performance in terms of input and output because the link between the instance and the instance store is a physical link. The size of this disk can range up to 7.5 TB and can be changed over time up to 30 TB at maximum. This is block storage, such as an EBS volume. Although it's in different arrangement from EBS network drives, well, for us in the console it will be seen as a hard disk. The problem is that the instance store cannot be extended in size. And there is a risk of data loss in the event of physical failure, where we have seen that with manual backups we can overcome this problem and create redundancy with this type of volume. Here we have an example of different instances and their possible input and output volumes. If we take a large instance, the X8 large for example, we see here that in reading it is at 1.65 million IOPS and in writing it is at 720,000 IOPS. With this type of volume you can really have a very high performance in terms of disk writing and reading. This is ideal for applications requiring very low input and output latency. Now we are going to go to the console to see how we set this up. For this, we will simulate the launch of an instance. We will choose as usual an Amazon Linux 2, and this is where we can choose an instance with an instance store. Here we have instance stores that are only in EBS, and here we have the choice, so we will take for example this one, the M5 AD large. We will go directly to the storage, and here we see that we have a root volume of an EBS volume in GP2. We will have here a volume ephemeral 0 of 75 GB. So we know that on this instance we will have our system installed here, and if you want to catch data to work on it, we can store it on this ephemeral 0 disk, which has high performance in terms of input and output. We are not going to create it because it's paid for. This is more or less the principle of the instance store, unlike the EBS volume.